It's my pleasure to welcome you to this 7th AI Valais Workshop, this year especially oriented towards energy. My name is Jerome Kempf. I'm a senior research scientist here at the IDIAP Research Institute, and I'm co-organizing this event with Professor Henning Müller from HSSO, who would like also to say some words of welcome to you all.
Yep, so welcome to this 7th workshop, as you already mentioned. So the objective of these workshops is really to bring people together and let them talk, and that's why we always have like a focused topic. So we've had food, we've had health, now energy, so I'm really looking forward to that. I'm not an expert in energy, but it should be a fun day. So we're ready for the first keynote talk, I think.
So for the program, as you can see, we have a first keynote, and then we have 4 presentations. We will have then a little break of half an hour. The idea is to trigger discussions between you, and we have also some people online following us on YouTube Live. So we have also set up a corner here for the questions online. We have Dr. Basurto, who will read the questions from the people online so that all the presenters can get the questions and also answer the questions of the people that are with us on the planet. Then we'll have 4 presentations and then a lunch break of 1 hour and 30 minutes, so also enough time to have hopefully interesting discussions. Then in the afternoon we have 2 bonus presentations from the CREM, here a research center in Martigny, and they also have booths, so during the break you can talk to them. If you don't have time to stay this afternoon to see their presentation, you can talk to them also during the breaks. So I think we can start.
Yep.
Yeah,
I think so.
So we are almost on time with the first presentation. So it's really my pleasure to welcome Professor Guglielmina Mutani from Politecnico di Torino. She's a professor and a specialist in GIS, and she will give the keynote for the first hour.
Thank you.
Thank you
so much. Is working the... Okay. Okay. It's not working. Okay, there. Maybe this one. No. Okay. 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 Okay, thank you. Okay, good morning, everybody. I'm Guglielmina Mutani. I'm a researcher, and I'm working in the Department of Energy at Politecnico di Torino. And today I'm going to present the title. I'm going to adjust the title afterwards, but the correct title is in the program. So I'm going to talk about the place-based model for sustainable cities and communities. After a little introduction, I will illustrate the most significant models that we use to represent energy consumption of the buildings at urban scale. And then I will describe some application of my current research. I'm going to talk about the place-based energy model, and particularly I'm going to use GIS tools, so tools with geographic information systems, and usually I'm going to work on different levels with information on different scale, but geolocalized. I'm going to talk about energy consumption model. So I'm going to describe all the building with the real characteristics, and I'm going to use these variables to build my models. Then I compare this energy consumption with the energy production system, the existing ones. And my work finished with the evaluation of the renewable energy sources that I have locally available. And finally, I use these three results of my work to build a decision-making platform with the aim to reach energy security, equity, and environmental sustainability. My models, the novelty of this, it's not a novelty, but the particularly of these place-based models is that I use existing database generally used by urban planners and available information, for example, the digital terrain model or digital surface model, or the technical maps for the cities, together with, of course, the climate data and the energy consumption data, for example, from the Sustainable Energy Action Plan or the newer Sustainable Energy and Climate Action Plan. The same for the production. I use the information available online. And for the productivity, also, I use all the information about the renewable energy sources available locally. Of course, the model I built depends on the main objective of the research. Usually, I do a monthly or hourly energy modeling. And with this place-based assessment, I can take into account all the constraints that there are on the terrain or on the city, like the technical, but also environmental, economic, and the constraints influenced by the law or regulation that there are specifically in each city. All this data are used to build a scenario, an actual scenario, or future scenarios, and that take into account all the input data, the modeling, and the constraints on the territory. And so I can evaluate the real targets that a city can reach with energy targets or environmental targets or economic targets. First of all, I'm going to talk about the type of approach that I can use. Generally, I use a top-down approach or a bottom-up approach, and this type of approaches depend on the type of data, mainly on the type of data that I have. Usually, if I have energy data at urban or municipal scale, I use, of course, a top-down approach. And then describing the built context, I identify some simplified energy modeling of the buildings, take into account all the information that I have at urban scale. And then I apply this modeling, simplified models at urban scale with some correction coefficient that take into account, for example, the local climate condition, the altitude, or other energy-related variable that I have on the territory. The bottom-up approach instead use some data that I have at building scale. This type of approach is more accurate. I can describe better the energy use of each building in a city. And of course, I can better describe the spatial distribution of the characteristic of each single building and of the built environment. The procedure afterwards is quite the same, depending on the type of variable that I have at urban scale, I identify simplified energy models of the buildings, and then I applied this model at urban scale, and again with I use also some correction coefficient to better spatially distribute the energy consumption, and then I can map the energy consumption with the correct spatial distribution. About the modeling, from the literature, the energy models of the buildings can be divided in process-driven models that are based on usually on energy balance, on the equation that describe the energy balance of the building, of a block of buildings, or district, or a city. They are based on the conservation of energy and the conservation of the mass. Afterwards, we have data-driven models that are based on statistics, which are widely used, and usually they involve regression techniques, so are quite simple, quite fast, and easy to use. Another type of data-driven models are the artificial intelligence, are the one that use artificial intelligence, like machine learning data-driven models. And this type of models can take into account also the complex patterns of real world, like, for example, the stochastic nature of human behavior, or some feature of renewable energy sources for energy production. We are working in the next future. We are working on hybrid models, which work on both process-driven model, but also data-driven models. Now we are using statistical models, but in the next future we are going to use also machine learning models to explain better some variables that are not statistically clear. Then the calculated energy consumption are compared with the energy consumption data. And so we apply these models at urban scale with a place-based assessment, like, for example, GIS. This is the first work that I'm going to present. It was made for the research project Citizen Power in 2010. Within Central Europe. The first, the conceptual scheme can be described with a GIS-based georeference database with all the information of the buildings. We are talking about Turin, where we have a big district heating network, so we have a lot of data about energy consumption. We built some energy models of the most typical buildings archetypes, also taking into account data from literature, like the research project Tabula. And then with these archetypes, applying some coefficient, for example, due to the more or less solar exposition, or more or less green surfaces that we have in the different parts of the cities. We apply this model at urban scale to describe the spatial distribution of energy consumption. Another model we have done for Gran Mendoza is quite similar. We start with in Gran Mendoza in Argentina. We started with the energy consumption of 6 departamentos in Gran Mendoza for 6 years. And we analyze the built environment, identifying the typical residential building types. And we analyze also the districts, selecting the district with a uniform type of buildings. Then we defined the energy intensity of this, the average energy intensity of these typical archetypes, and we apply this energy intensity at urban scale using some coefficient. For example, in Gran Mendoza, we have a lot of difference in altitude, so to adapt our model at different altitudes. And then we compare the energy consumption that we have with the first data for the departamentos. These were top-down models. Here we have a bottom-up model that we applied in Turin within the project Empowering. And here we have a lot of data about the buildings, a very accurate database with the energy consumption of more than 2,000 buildings. We adjust the databases, completing the empty data and removing the outlier with statistical analysis. Then we identify the average energy consumption intensity of the buildings, for example, for a period of construction, but also depending on the compactness of the building with the surface to volume ratio. And those type of models were accurate enough to evaluate also the energy saving potential in short, medium, and long term. Like, for example, here we can see that for Turin, which is an historical city with a lot of constraints, technical, economical, and environmental constraints, because we have an historical center, so we cannot do retrofit intervention of the envelope. We have some constraints because we have a district heating network, so we cannot change the boiler of the buildings. But as we can see, in other municipalities around Turin, there are much less constraints, so we can group together the different municipalities to improve the energy saving potential. This is the main concept. Here there is another project, a bottom-up project that we have done in Settimo Torinese, which is a little city near Turin with less than 5,000 of inhabitants. The principle is quite similar. We did this work within the project, an Italian project, Zero Energy Building Smart Urban District, co-financed by the Ministry of Education, Research and University in Italy. The concept is quite similar. We did a data collection and integration database with GIS. Here we can see, for example, the period of construction and the surface to volume ratio of the residential buildings in Settimo Torinese. Then we identified the energy-related variables, the more energy-related variables, taking into account the information available for each single buildings in Settimo Torinese, and we did the modeling and the validation. And afterwards, we applied this modeling at urban scale with a GIS tool. After step 1, so the data collection, we use a rapid miner, which is a statistical software, to evaluate the best multiple linear regression. The variables that were influencing the energy consumption were the period of construction, the heated volume, the type of ground floor with commercial or other type of use for the ground floor. The occupancy rate, the air temperature, this is a monthly model, the type of roof, and the boiler power. We reach a coefficient of determination of 0.84 and 0.83 if we do not consider the last two variables which were not available for the whole city. But as you can see, there are some, this regression is not good for very high volume buildings. We control also the significativity of this multiple linear regression with the p-value for each single variable, and which is lower than 5% and an high F statistic value. And here are some of the results of the consumption for each single building. The same type of model was applied for the metropolitan city of Rome. In this case, this work was made with, in collaboration with La Sapienza University of Rome. We used some data about 7,000 of dwellings from questionnaires given by University La Sapienza of Rome. But we use also the ISTAT census database and the municipal technical maps to describe the geometry of the built environment. With the Pearson coefficient, we evaluate the more energy-related variables for the energy consumption model for space heating, space cooling, domestic hot water production, and electricity. The multiple linear regression that we obtained were quite good, with an high coefficient of determination higher than 80% and a good significance with a p-value lower than 5%. We applied then this linear correlation on the built environment at the municipal scale, and we compare the energy consumption with the data of the Sustainable Energy Action Plan and the newer Sustainable Energy and Climate Action Plan. And then we did the validation and the GIS Energy Atlas. Here there are some pictures of the building period of construction, the surface to volume ratio of the buildings, and the number of inhabitants per gross volume that were used for the different models. Here are some examples of the linear regression we obtained. This is the one for space heating, using the period of construction and the surface to volume ratio. Here there are the p-values of these two independent variables and the whole significance of the multiple linear regression, which are much lower than 5%. And this is an example of the electricity linear regression analysis that we have made, which is influenced by the energy performance index for domestic hot water production and the energy performance index for space cooling. And again, we can see the p-value for the both variables and the analysis of the residual, of the variance of the residual by these two independent variables. This is now we are going to talk about engineering models, so physical-based model or process-based model. In this case, this is a top-down model. We start with the energy consumption for the city of Turin for 48 meshes of 1 kilometer per 1 kilometer. and we applied an engineering model based on a quasi-state monthly energy balance, as explained by the Italian standards 11,300. As we can see, we applied this type of energy balance at the district scale, not at the building scale, using some, of course, variable like the sky view factor, the canyon effect with the height to width ratio between buildings, and the main orientation of streets. These variables were very important to explain some data that we don't have at urban scale, of course. The steps of this to create this model is quite similar to the one I explained before. First of all, I have to collect the data at building scale, at block of building scale, or at district scale, like the building data, the climate data, and the urban morphology data. We collect this database with a GIS tool to represent exactly the built environment. Then we use these variables to create the energy balance model. Of course, we use neighborhood scale data, so we built these variables using also urban data. And we calculate the energy performance into each mesh, and we compare this value with the measured data on different, of course, season, monthly, on different season, and if the two indexes were not comparable, we calibrate again of course, the variables. We check the different heat fluxes to understand the problem, and until the two indexes were comparable, and then we applied the model at urban scale. As an example, here we have the sky view factor that we used, we can calculate at urban scale with a GIS tool. Of course, the sky view factor influences the solar heat gains, but it influences also the extra flux of the built environment to the sky. And beside the sky view factor, we use also the average height of each single building and the main street orientation at the block of building scale. These are some results for two meshes for space heating and domestic hot water of different period of construction. And here there are some results. As you can see, the mean absolute percentage error is quite low, but higher, of course, error can be observed for some untypical meshes where we have a low percentage of residential building connected to the district heating network, a high percentage of green areas, or high values of albedo, which are untypical for this type of urban context, and high building coverage ratio, low sky view factor, and low values of relative height of the buildings. The engineering model on which we are working now is an hourly model based on energy balance of three thermodynamic systems that we have on the built environment, and specifically the opaque envelope, the transparent envelope, and the building, like internal structure, furniture, object, people, and air. These three systems influence one each other, and so it was built an iterative procedure to solve this energy balance of these three systems, but quite simple with an Excel spreadsheet. The input data are quite the same with the GIS database. We did this balance for each single buildings, taking into account all the specific characteristic of each single building, and we applied, applied this energy balance at block of building scale. These are the clusters that we analyzed with the information on the hourly energy demand for space heating in green. But as you can see, we have all the, this is an example of a typical winter day. But we can see that we have all the heat fluxes for the internal heat gains, the ventilation heat gains, the heat losses by the transparent envelope and the opaque envelope. And so we can understand if there are some errors where there is a low accuracy. The average seasonal relative error with this model was of about 14%, with better results for the three first clusters, in which we have more, this is a mesh, the results of a mesh, with more buildings and more data. The aim of this work was to prepare, organize, project a decision-making platform like this one, in which we have we can compare the characteristic of a district like this one, and then to evaluate the energy targets, the environmental targets, but also the thermal comfort condition, changing some variables, like for example the building density, the use of the roof to produce energy with photovoltaic or solar thermal collectors, to use the green roof with green roof technologies, and to compare the thermal comfort condition with and without urban green surfaces. The same hourly energy model was also validated for the cooling, space cooling consumption. And here there is an example, a quite clear example of the, for example, of how we have calculated the shadow surfaces of the building envelopes at the block of building scale, taking into account for each hour the sun height, but also the height to width ratio of urban canyon. Of course, we work with the same three thermodynamic systems, and we compare the results of our GIS model with CitySim and with ISO standard 52016. We calibrate the model at building scale. Here there are some typical hot days during the year, even if Torino is not so hot as an Italian city. And once the model was calibrated, we applied to this model to typical block of buildings that we have in Turin. And we can see that the model works quite well, but not for the block of building with towers, which is a particular, not very used in Italian cities. And now we are working to improve the heat flow rate by ventilation, because in the previous example we used an air changes per hour constant with 0.3 or 0.5 depending on the type of windows, the period of construction, and so on. The aim of this work was to calculate average monthly air changes per hour, also depending on the air permeability of the windows, considering that during the night usually the air permeability is lower, and in the last scenarios when the air changes per hour is too low, probably we open the windows. Here there are some results. This first work was applied to two buildings with different orientation, considering the main wind direction during the winter month and the air velocity. Here there are the results for a wind-exposed building, this one. And here we can see how the air changes per hour changes during the different months with very low values in October and in December and January. And while this air changes per hours changes by 41% during the other month. We did 4 different scenarios, as I said before, and here are the main results showing that the changes of air change per hours can improve quite well the energy consumption results, even in a city like Turin with a very low wind velocity. Finally, this is one of our last works in which we compare a machine learning model using light gradient boosting with our GIS-based engineering model and also with CitySim. We adjust our GIS-based engineering model with some statistical improvement. And we apply this comparison to the city of Fribourg. We did a sensitivity analysis with the Morris test to check which are the variables that most influence the energy consumption. And so we adjust the models taking into account mainly these variables. And we can see that the air changes per hour is quite important to analyze these models. And here are some comparison of the 3 models for some days, typical monthly days in Fribourg. These are some of the work we have done with our model. We applied a monthly engineering model, for example, to check which is the potential expansion of a district heating network in the actual scenario, or in a scenario with standard or advanced retrofit intervention with in different network and where we can connect more users, of course. This is another application. For example, we can, basing on the constraint that we have on the territory, define a priority of intervention, basing, for example, our priority on the air quality and outdoor thermal comfort conditions. And in this case, for example, we applied where the air quality is quite low, we applied the potential green roof, of course, on the flat roof, while when the roof is well solar exposed, we can produce energy or decide to use the low emittance surface, but with thermal insulation. We are doing also some work with outdoor thermal comfort condition of our solution. This is an example of some simulation we did with EnviMet, comparing a typical summer day with and without the green roof. So we can see how the surface temperature changes. The aim of this work is again to find a fast solution, to give some solution, a good solution to improve our urban environment. We compare the results with the mean gradient temperature, which is for the outdoor environment the main variable that influence thermal comfort condition. We compare the mean radiant temperature using CitySim, EnviMet, and Solveig, and simplified equation with GIS-based information. And as we can see, there are quite big differences between the models, but our GIS-based equation seems to work quite well. How much time do I have? 10, okay. Of course, our models are made to check the energy performance during both season, heating and cooling season. And in the last years, we are working also to evaluate which is the best urban morphology, the morphology of the built environment that can have a best energy performance, but also the best morphology to produce energy with solar technologies. This is an example or how we work. This is the solar resources on the roof of the buildings that we can calculate. Of course, as you can see, as you saw before, we can do the models about an electrical or energy consumption. We can match the two information to get the best solution to produce energy, taking into account the energy consumption, and check the self-sufficiency or energy independence of that territory. Also grouping some users together, for example, in energy communities. And this is an example of a typical district with the residential consumption, photovoltaic energy production, and the energy production of also other users. This is some of the evaluation that we have done in the bottom graph. As you can see, we have tried to analyze the energy production not only in the roof with on-south exposition, but also the part of the north roof, north-oriented roof, and to improve the self-consumption hours. And so this was one of the results of this analysis. So not only south-oriented roof, but also a part of the north side, because the residential user have a high consumption during the last part of the day, especially in the afternoon. This is another work we have done. we check in some, we analyze some typical built morphology in 6 districts in Turin, and we compare the compactness of the building with the energy production potential using the roof, so with the ratio of production to consumption. And as we can see, of course, we have a higher production to consumption ratio with higher surface to volume ratio, but with higher surface to volume ratio, we have also higher energy losses by transmission. And so we have to match these two information together. We are doing some workshop on these models every year in Turin. So they are open, this workshop are open to all the students who would like to participate. And I can conclude with some strengths and weaknesses of the various approaches, top-down and bottom-up, and strengths and weaknesses of the different models that we saw. I will leave this, or can I comment a little bit? Okay. Sure. Of course, the top-down approach is very simple, and we have already all the information to do this type of approach. The weaknesses is the difficulties in differently apply the spatial information on a territory, because we don't have the models usually do not take into account a spatial variability, if not with simplified correction coefficient. The bottom-up approach is much more accurate. Of course, we need a lot of data, and we can use energy saving also potential analysis with this data. Of course, the data collection is long, very difficult, and sometimes not possible. This certainly is not online, the data of this, for this approach. About the models, I can say that the engineering models is my preferred, but because of my, probably, my formation. This approach doesn't need a lot of data, and consent to improve the accuracy, specifically with an energy balance. And then changing some variables, I can also simulate future scenarios. Of course, it doesn't take into account, or is difficult to take into account some factors like human-related factors, like human behavior, while statistical is the most used model. Because it's user-friendly, it's very simple and fast to apply. Machine learning could be a good model, because with this type of model we can take into account also some aspect of the real world. Of course, we need a very big database, and so, of course, as all the models, the range of application is very important to check. I would like to conclude that, of course, I didn't talk about all my collaborators. Without them, I could not manage all these models and all this data. So, of course, I would like to thank, it's not only my work, it's a work of a group, and but you can join if you want with our workshop each year in Politecnico di Torino. Thank you.
So thank you very much for the very impressive presentation. Do we have some questions from the audience? Yes, so I come to you with a mic so that people online can also listen to your question. Okay?
Thank you very much for this presentation. You presented potential of a green roof on GIS, on solar energy analysis. Did you combine both? So a green roof plus solar panels?
We did not this evaluation because in Italy green roof are the cost of installation and the maintenance is very high, and so cover the green roof. it's too expensive for our application, but we decide to analyze this type, the priority of intervention with green roof, where there are a critical condition about air quality, and spend lower money with solar thermal collectors in the other part of the city.
I was more wondering about the solar photovoltaic panels.
Yes.
On the roof.
Yes, we did this analysis, and we with this type of models we define where is a cost-effective solution, deciding also where to install, which are the good surface, how to dimension the system, take into account the different solar exposition, and take into account the possibility to install also some storage systems to improve the economical feasibility of the intervention.
Thank you.
You're welcome.
Thank you for this question. Chantal, do we have a question online? No question online?
Not yet.
Not yet?
Not yet.
So we have a question in the room.
Thank you very much for your talk. I have a question about your relationship between utilities companies and your planification. So how does it work? So can you really transmit what you have planified to the utility companies that have to implement it?
Yes, because they did not have this information. They work on the mass flow capacity of each branch of the network, but they don't know the potential connectable volume of the buildings, and even they don't know the type of user, so they don't know the load curves of the heat demand. And so we gave them this information. I was talking with somebody, I don't know who, maybe you, and we are working on the supply, on the energy demand, and then we give this information to the energy supply expert that works on the capacity of each network, of each branch of the networks. And also we give the information of the connectable volume, of how the connectable volumes changes if we apply some energy retrofit interventions on the buildings. This is how we work.
Another question in the room? Yes.
Thank you. On the methodological side, you mentioned on the one hand that on a side that thinks, okay, what happens when the person opens the window? I had the impression that your models, as they are kind of mechanistic, process-oriented, their buildings are actually all pretty empty. I mean,
no, we take into account the occupancy rate of the buildings. Yes, this is very important, not only for ventilation, but also for space heating demand.
But not things like, I mean, people make a distinction between weekdays and weekends, but your buildings don't care in that sense, right?
No, I have a different load also between not only weekday and weekend days, but we have also differences during the day and night.
Okay. So there's
About,
kind of a curve that
Yes,
simulates.
yes, some information about internal gains, that the variation of internal gains. We did also this, we give this information also for the machine learning analysis we did in Fribourg, changing the occupancy rate of the buildings.
Could you might also say a little bit on how you calibrated your models? You mentioned only once that in one side sentence there's calibration, but I mean, normally that's one of the big out parts in making the model work.
Yes, because there is a lot of things to do to say. It's the most important part of course of the work. We try an energy balance equation, and then we start the calibration. We change the variables. We use some variables, and then we modify them. We applied some variables at urban scale, like the sky view factor, as an example. And we introduce these variables in the different variables in the energy balance. And then we work changing the different variables. Of course, first of all, we do a sensitivity analysis to check which are the main variables that influence energy consumption. And this, of course, helps a lot in doing this calibration.
Yeah, I assume otherwise your space for calibration, your search space, become a little bit too big, because you have a lot of variables. How much variables, do you have an idea how much variables are there in the calibration process?
Like, for example, I want to say the example of Rome, the questionnaires that we have on about 700 of questionnaires. Each questionnaire has 200 variables. But of course, we are going to take into account only the main variables. This is the point. And so that we go on building our models.
Okay, thank you.
You're welcome.
Thank you. I think we have time for one last question. Chantal, do we have a question online? No, still the same? Please don't be shy. Don't hesitate to ask questions, especially if you just have to type the question. You don't need to be shy. Do we have a question in the room? No question in the room?
No.
Then I will ask myself maybe the last question. So do you have also access to, let's say, monitoring data of energy consumption that have a sampling rate of an hour or below the hour?
Usually, like for example in Turin, we have 15 minutes, like electrical energy. But we use an hourly model because it's already enough for our hourly model, and especially for thermal energy, in which you don't have very quick differences to check. Lower the hourly time step for thermal energy is too low. But we don't go below the 15 minutes.
Okay, because indeed, when you start going to fine in time, then it's also the way the system works.
Yes,
that
the
has
way
an
the
effect.
system answer. Yes, no, but probably because we work on the energy demand side, not on the energy supply side. Yes,
So
probably.
Going until 15 minutes is fine.
Yes, yes. For me, and for the energy supply researcher with which I work, they they tell me that it's fine. But of course, it's an iterative, for example, engineering model, so I can use whatever time step I want. This is one of the goodness step of the engineering model.
So thank you very much. So
You're
once again, I
welcome.
think Professor Moutani deserves a round of applause.
Thank you so much.
Thank you. So now I will call the next speaker, so Roberto Boghetti. Roberto Boghetti is a PhD student, both at EDF and at EPFL, and he's going to talk about district heating networks and how actually we can do some physics-informed neural networks or something similar.
Yes.
So thank you, Roberto. I'll just let you grab your presentation, and then you can start whenever you want.
Okay, so hello everyone. The work I'm presenting today is part of a big project. It's a small part of a large project which is called EGUTSKI, and it's supported and financed by several Swiss companies and institutions, which I would like to thank. So I will just start by giving you some key facts about distributed networks. Distributed networks are are networks of insulated underground pipes that distributes the heat from a centralized or more than one actually centralized locations to several customer buildings. As you can see in this illustration, they have two lines, a feed line that goes from the heating station, in this case, to the buildings, bringing hot water and therefore energy to those buildings. And then a return line with cold water that goes back to the central station where it is heated up again. The system can become easily very complex and big. This is actually not one of the biggest ones, but you can already see some complexity. It serves a lot of customers, it has a lot of loops, and it has several heating stations also. And simulating those systems is kind of difficult. Why they are relevant? Distributed networks are relevant because they are very efficient systems, and they have the potential to decarbonize space and water heating. So they are central to many climate change strategies and reports. This is an example of the use that is forecasted for industry in 2030 by the European Union, and in some countries there is an expected growth at least of those systems to match the targets for 2050 and whatever. One big problem of these systems is that they are kind of hard to simulate because they will require two loops to do physical simulations. I'm not going to annoy you too much with the equations, but basically they will, usually the physical-based simulation method follows the same frameworks with different equations, but it's exactly the same framework. So we make some guesses on the opening of the valves, which is the KV, and the rotational speed of the pump, which is the N, which you can see there. And then we start computing the hydraulics of the system. So again, we make some guesses, usually on the mass flow or on the pressure differences in the network. We build a system of equation using those guesses. It's a very complex system of nonlinear and discontinuous, especially equations, due to the Darcy friction factor, if you want the detail. Then we try to solve this system using the Newton-Raphson method, which is an iterative process. So basically, we compute the Jacobian matrix, use this Jacobian matrix to build a linear system and find a correction factor, let's say, for our guesses that we apply to the mass flow or delta P that we guessed. And then we compute the error, and we start again the step from the first. We start again the hydraulics simulation until it converges. Then we can see if our guesses on the KVs of the valves and the rotational speed of the pumps were right. Otherwise, again, we change those guesses and we start again from the start. So the key takeaway here is that basically the simulation of those systems is very complex and computationally expensive. So the problem is that it is slow, not that it's difficult itself. So that's why we might want to use machine learning to try to have a faster way of doing not really simulations, but at least inference on what could be the state of our network given some constraints. So the naive, let's say, approach of machine learning in this case would be to pick a case study, fix some architecture of our distributed network. So we will take a fixed number of pipes in fixed position with fixed length and fixed diameter. We decide some days that we want to simulate, so some energy demands basically from the buildings that are connected. We run those simulations with physical-based softwares like CitySim or Panda Pipes in this case. And then we use the same inputs that we have used for those models and the outputs of those models to train a neural network or a machine learning model in general, so that hopefully it will be able to make prediction on new data, on new energy demand in this case for the same network. So this approach, as I've said, has the advantage of being very fast once that the model is trained. However, it has some disadvantages, so it requires a lot of data. It's very hard to generalize such model because what we have done is to take a fixed network architecture and make a model for that architecture, for that particular distributed network. So it doesn't really generalize to a new network. It's a completely a black box, so we don't know what is happening inside our neural network, our machine learning model. We just know what is going in and what's going out. There are some techniques to have an idea of what is happening, but still it's kind of a black box for us. And the main disadvantage is also that we are not exploiting the domain knowledge that we have. So we know what are the physical constraints of the problem, but we are just disregarding this knowledge and not using it. So that's a waste. Another maybe smarter approach would be to use what's called residual physics neural networks or physics-informed kind of neural network. It has several names, but basically what we do is, again, we pick a case study, fixed. We generate some random inputs for the energy demands. So we have some fixed inputs, which are the network architecture characteristics, and some variable inputs that is the energy that is requested by all those substation or those buildings. Actually, we can do something smarter and not really generate it randomly, completely randomly, but let's take it like it is for now. So we put those inputs into a neural network, and then what a neural network does usually during training is learning how to minimize, let's say, a function. In the previous case, the function was the error between our simulations and the prediction of the network. In this case, our loss function will be some kind of physical constraints that we need to minimize. So the advantages of this approach is that, again, the inference, once that the neural network is trained, will be very fast compared to physical models. It doesn't require to do simulations beforehand, and it's a little more explainable than the previous approach because we can have, for example, intermediate quantities that we compute in our network. We don't really need to have only a neural network full of neurons that we don't know what they are doing, but still it's not 100% explainable, so it's halfway there. And again, the disadvantage of this approach is mainly that it's very hard to generalize. Of course, we can change the inputs and devise a network that can take any kind of distributed network as an input, but then it will be a very, very complex model and it will be super hard to train. So that's hopefully our goal, but it will take time. So for now, let's say that it's hard to generalize. So I will just give you a simple example. In this case, actually, you may not need to do the double loop simulation, physical-based simulation, because it's just a tree-based network, but it's just to give you an idea of, and then we will build up from here. So again, we will have some inputs, the fixed network topology, characteristic of the pipes, and the variable energy demand of the consumer. That's the only thing that changes basically from one sample, let's say, to the other. The outputs that we want are the mass flow in each pipe and the pressure losses in each pipe. the constraints that we will use are the conservation of mass. So basically, whatever enters one node has to exit that node, not more and not less. And we want that the energy delivered at the consumers is what they asked for, basically. So for the conservation of mass, we can do something pretty interesting. So instead of putting this constraint in the loss function, we can put this constraint into the actual network. So I don't know if any of you knows about cycles in a graph, but basically the network is exactly a graph made out of nodes and edges. The edges being the pipes, the heating stations, and the buildings, and the nodes being the junctions, basically. So we can find some cycles in a graph, which are path that goes from one point to itself without meeting the same edge twice. And we can also find a subgroup, let's say, a subset of these cycles from which we can build by superimposition all the other cycles of the graph. And if we can estimate the mass flow into these elementary cycles, as they are called, by superimposition, we can find the mass flow in each element of our network, and it will automatically preserve the conservation of mass, basically. The second constraint that we will give, and this is actually in the loss function that we want to optimize for, is to satisfy the energy demand of the consumers. In this case, we can explicit this constraint in different ways. It could be a mean squared error on the values. It could be whatever. But what is the key takeaway here is that we are not using any simulation data, just those constraints to train our network. So as you can see, the training of this network is pretty fast. Again, the network is very small, the discrete network, and it's very easy because it's a tree-based, it has no loops. But with only 4 to 5 minutes of training, we have a model that can output a full year of simulations, hourly simulation for one full year in less than 1 second, in 0.25 seconds, while a physics-based approach will take 3 minutes, around 3 minutes. We can extend this to loop the network, as I was saying, by introducing new and more physical constraints. In this case, we have the an analogous of the Kirchhoff's second law in the electric circuit. So basically, we know that in our pipes, edges in general, we have pressure losses or pressure lifts, especially if you have a pump. And if we take an elementary cycle or a cycle of our network, the directed sum of all those pressures, losses, and lifts should be equal to 0. So that's something that we can optimize for. Because of course, when you have a loop, you don't know a priori where the flow is going. So when the loop starts, it can go left, it can go right, or it can split. And it depends on the pressure differences inside your network. So that's what we have done. As you can see, there is learning curve for the network, which takes a bit more because it's more complex than the previous case, but still it's a reasonable amount of time. So thank you. I hope it was interesting.
Thank you, Roberto, for the presentation. So we just have time maybe for 1 or 2 questions. Do we have a question in the room? Yes? I'll go first in the back.
Hello, thank you very much for the nice presentation. I find it very interesting, these physics-informed approaches, but have you actually compared it to the original approach? Because I've discussed with some people who actually often find that physics-based approaches, they take so much longer to train and practice that in the end, the gain you get might not necessarily justify it. And my second question would be, how much is actually the gain if we include the data pre-processing for the training data set, rather than just the modeling approach itself with a neural network?
Okay. So, of course, as you were saying, the training of those networks is kind of longer than with typical approaches. But you have two advantages. The first one is that you don't have to make simulations. And when you make simulation, of course, you have to plan what to simulate and have samples that are enough, spaced enough, let's say, one from each other, so that your network can train reasonable big problem space. And the second advantage is that by imposing some physical constraints, you are, let's say, a little more sure that it's actually doing what it's supposed to do, and it's not just throwing predictions of something that has remembered, for example, or that was biased by your training data, let's say.
But you compared the two and you actually got better results for the
Yes,
physics
actually, I've compared the two and I got slightly better results with the naive, let's say, approach, the classical approach. But then again, it was performing very well on a small range of input values. But as I was to extend that range of values, it was not performing as well, to be honest. So, of course, the training time was much lower. So you can think of a model that is specialized for a small range of values, but then that's not really interesting.
Thank you. Unfortunately, we are running out of time. Chantal, do we have a question online? No. Fantastic. I was hoping you would say no. Right. So I think it's time to call for the next presenter. So I'll let Professor Schumann from HSSO to do the moderation of this one.
So, hello. Go on stage. So we now change perspective in at least two dimensions. We go from the demand to the supply, and we go from the bigger things, so from the districts more to more specific things on the plant side. And now, hopefully stage is in a few milliseconds yours. The short interruption, we need this animation.
Okay. So hi everyone. I'm Amin. I'm a research associate assistant in the both Institute of Energy Management and Energy and Environment of HSSO. I worked there since around a year. I'm holding a bachelor degree in energy, and I had followed some courses in data science. So today I will be presenting the work of Francesco Cimino, which is a colleague of mine in the lab, and he apologized for not being here today. So I want to mention that I'm not author, neither co-author of the work. So I took the freedom to split the presentation into two parts. First part more about his paper, and then the last part about some project related to AI and energy in our lab that I'm working on. So, as I said, I recall the first part is this paper from Francesco Cimino. It's a paper that composed his doctoral thesis that he will be defending in December. And then for the second part, as I said, a few projects related to AI and energy that we're conducting in our lab. So Francesco holds a double master in statistics and econometrics, and he is working for around 4 years in the lab, and he will be defending his thesis in December this year, next month. So the paper entitled Machine Learning Forecast for Photovoltaic Power Station with Spatial Interpolation on Cosmos 7 Model with a use case in Czech Republic. So a company, an industrial, asked them if they could improve forecast of their around 150 and 200 PV station localized in Czech Republic in many locations. And they had as constraint no real measurement data of weather in the site location and very few or no characteristic of this installation beside historical data. So first, they will use the Cosmos 7 model, which is an atmospheric prediction model from Meteo Suisse based on physics equation. We can have a glance on the table that is returned by this model. He is computed or provide hourly prediction, some like cloud coverage, radiation, solar radiation, temperature, like very classic features, let's say. And the PV production on site of this 150 around site are hourly basis for around 1.5 years. So at the time in 2017, according to the state of the art, some paper would have physics-based modeling for the forecast, some also with neural networks, and as features different many techniques. I will not go into details, but some of them also use already meteorological satellite data, and voila. So to sum up the methodology, it's a very common, let's say, pipeline, and with a first step of pre-processing the data, cleaning, handling missing values, and so on. Then the main idea in this paper was to interpolate the meteorological data obtained from the Cosmos model into the PV location site, and with other common feature engineering technique, and then used 4 distinct model: autoregressive model with seasonal and exogenous values, some other neural network architecture at this time. So quickly about the methodology. So inverse distance weighting was used to interpolate the meteorological data from Cosmos 7 into the PV location. He had around 4,000 points above Czech Republic, and he does use this point to interpolate at the location. Then he evaluated autocorrelation function to evaluate the lagging importance of seasonal autoregressive mean average model, and then the feature covariance or correlation of the meteo data. Then for the result, here on top left, we can see an example of single output, single step, but for a test set around 250 time step. And he evaluate or compare the different metrics, and specifically the root mean square error divided by the max value. And he obtained quite similar result with the different models. And he then compared this result to the other papers obtained, but by averaging each models. And he analyzed that, or he noticed that he obtained quite smaller or a little improvement in the accuracy of this combination of model. And he tried to explain the result by evaluating the different distribution of the residual of each model. So here for So I invite everyone for any further detailed question about any of the topics to write to him. And some projects in our lab related to AI and energy, both are Inno-Swiss project with different partners. And the second one is specifically with also many other academic partners. One of them is delocalized energy forecast for smart grid, which is kind of similar with the presented paper, but in different location and with different goals. But the idea here will be to use a graph neural network with hyperlocal meteo features, and to again try to predict this time multi-output and multi-step for different goals or values. And the last project is a clean energy exchange, which is with also these many partners. The goal here is to develop two platforms, and the idea is to make possible peer-to-peer energy trading in local communities. And there will be one platform for DSO to manage this local energy market, and a participant application for each participant in the market to be in this market. And this project is specifically taking into consideration many layers of constraint, physical, economical, and technological, as we are also targeting to certify exchanges with blockchain. And just a bit more in detail, the DSO part or platform will have as objective to input dynamic grid fees pricing advisor to steer market in some degree. And the participant application will be driven by automated agent strategy, and to be selected by the participant, and hence therefore have many different objectives in this trading. So thanks for your listening, and
okay, thank you. Exactly. So questions. I mean, you defected already quite elegantly from the first part. I would. Since next week Wednesday I'm in your office, I will collect all the questions and ask you then. No escape. So please don't hold back. Okay. So first, thank you for your presentation.
Thank you.
So, questions. Don't hold back. As pointed out, next week, latest next week Wednesday, I will meet these guys, and then I will ask all questions in your name.
Great.
Do we have a question on the internet? Okay, so I will ask for. So since I will not ask for part one,
Yeah.
I will ask them, but be aware, I will ask them next week Wednesday.
No worry.
But for part two, I can ask questions.
Yeah.
Good. Then the default question: why blockchain, and what shall come out for using that?
Well, this was defined by project leaders first, and secondly,
You're deflecting again. No, we want answers, no deflections here.
no, it's because when you are in a free market and you want to trade energy, you need to certify transaction between actors, and therefore using distributed ledger technology to certify this transaction, then you can monetize. Well, yeah.
Okay, so then let's go for the next speaker. Where is he? Where is the person?
Thank you. So the next speaker is Dr. Giuseppe Peronato from EDIAP, and he's going to talk about heat learning.
Is it okay for the mic? So yeah, as Jerome said, I'm going to talk about this project named HeatLearn. The idea is to go back to the one fundamental research question in urban planning, which is how does the urban the urban fabric performs, and so find the determinants of the performance of a city based just on the urban morphology. So in this case, we are going to start from a very energy perspective, which with a question that is what is the aggregated heat building demand of a given urban area? That's a very generic question, but it's very useful because it's the preliminary question that should be answered before planning any large-scale energy system in a city. For example, district heating networks, we have to we need a minimal heating demand from the buildings for this system to be economically viable. And then there is a problem. This is a problem that has been already addressed in the literature, usually with an engineering approach. And this engineering approach have the disadvantage that they need several data sets. And maybe I didn't mention that we are gonna, the goal was also to apply it at the large scale, so the continental scale, for example, Europe. And so we need data that are available for all spatial location and similar so that we can have a consistent approach. So yeah, this is just an example from an existing project from the literature where you see all the needed data to perform the engineering model. And then the research question is another research question which is more on the machine learning perspective. So can machine learning on the land use maps, which is these kind of maps that are available for the entire European Union and including some other countries like Switzerland, can machine learning on this data set outperform engineering models as the one we've seen before? So that was the fundamental research question. And to go further on the on the context of this project I'm presenting, so this is a part of a research project called EnerMaps. You've seen maybe outside the booth by our colleagues from CRAM. And you're going to have some presentation this afternoon, but just to introduce why we did that. So, and what is EnerMaps is a web platform for mapping selected energy datasets, which are listed in the OpenAir repository, which is a scientific repository for the research community. And as part of this platform, we have several calculation models that make use of these datasets available in the platform to run on-the-fly analysis. And the idea was to develop a calculation model based on machine learning using then the European settlement map as the input, which is one of the datasets listed in this platform. So yeah, the European settlement map. So here we have an example. He's kind of noisy, and yeah, it's not very high resolution. Each pixel 2.5 meters. But basically, what we can extract is the morphology of the buildings, of our urban area. And then we train our model using some data sets from heating demand, which are available in the canton of Geneva, where buildings are required by law to give their annual heating consumption to the state. And then this data is very interesting. It's a very unique data set, I think, in Europe. And then we can train a model based on this data. And then, of course, we have more cadastral data, which give us the shape of the buildings and the footprint of the buildings and the total floor area. So we train our model on this IDC from French, on this the Dépenses de chaleur, which is this building heating demand data set. Yeah, the predictors, as I said, is the European settlement map, but then we added a mask where to tell the model where we don't have data from the Geneva dataset. Because, yeah, I didn't mention we have about 1/3 of the buildings for which we have this data, which is still kind of a lot. But yeah, for each area, we don't have all of them. And then, classic approach in this kind of work, we work with tiles, regular tiles. Then the tiles are overlapped to augment the data we can train off. And then we also flipped this tile to have more data to train our model. And then we trained CNN using the two input images, the mask and the European settlement map. And then the resulting information is the one-by-one information is the annual heating demand for each tile, so aggregated at the tile level. And then with this first approach, we compared with a baseline model, which is a polynomial regression, and we see we improve the results. This is on a 300 meters tile. And then the question is also whether what is the accuracy at different tile levels, and these are results for different resolution. So as you see, the larger, the better, which is kind of maybe intuitive. But this probably means that we have a kind of low error for 500 meter tiles. This probably means that the Geneva urban fabric is pretty consistent within this range, and it averages out the possible differences of usages that we can find in these areas. And then we compared with this reference engineering model I presented before. So as I said, based on an extensive number of data sets, and the accuracy was not available, so was also the idea to test accuracy in the Geneva area. Two data sets from this project were used, one for the actual heat density and one the gross floor area, which is, both are raster models at the 100 meter resolution. And we first adapted the data from this engineering model to be compared with our model from Geneva. So a correction for weather and a correction for the area, which was not necessarily the same between the Geneva datasets and the hot maps datasets. And then this reference engineering model was on 100 meter tiles. We've seen before that the performance was not very good at 100 meter tiles for our model. So the idea was to improve the performance, use a context-aware model where we feed our model with some information about the surrounding area. So we want to predict the center of the tile, the 100 meter tile, but we give the model the information about the larger tile. And the results, so compared with our model with the reference engineering model, the performance could say it's kind of similar, but we have to consider that, I mean, this is not a completely fair comparison because the engineering model was has a much more input data sets, while we rely for our model just on the European settlement map. And so, these are the errors that should be expected for the 100 meter, but we've seen before that if we go to larger tiles, we have a much better results. And then maybe something, this work was presented in a poster and at CISBAT conference in September, and since then we deployed this model online, and so I'm very happy, I mean, to be able to present to you this model at CISBAT was just a poster, but also to see how does it look like when deployed in the EnerMaps platform. Just a few words about the methodology or to bring this work online. The idea for these calculation models in EnerMaps is to to be able to show how we can, for example, use the deployment of a machine learning model, how can it work online with data sets from the Nrmaps. So we used the Docker architecture, and then we have an architecture that managed with an API managing the inputs and outputs from the calculation models. We use asynchronous tasks run by the user, so we can support multiple users running the task. And basically, the user selects the European settlement map as the input, the boundary for their analysis, and then the heat-learn calculation model deploys the TensorFlow model, but also uses the heating degree days from the Nrmaps database, which come from Eurostat. And then, as the output has this, the map and some summary statistics about the area. So there are some limitation about this work. This model has been trained only on Geneva, so we have to be careful of the difference that might have in other areas. And then we neglect also the usage of the buildings, except for what can be extracted only from the building morphology. And then, the application is limited to EU countries, so unfortunately not Switzerland, because there are no heating degree days from Switzerland in Eurostat. But we added some data for the Geneva area. And then some low density tiles are excluded, but they would be not much interest anymore. So maybe, I can show in the minutes I have left, I think, how it works online. And if you want, we select the European settlement map as the input with zoom. Then we see it when we zoom in. We can select some boundaries for our analysis. In this case, we see the municipalities. Then we select the resolution of our analysis. In this case, it's 400 meters. The year, 2020, because we can use the historical data from heating degree days from Eurostat, and then we run our task. It takes a few seconds, depends on the size of the area, and then we have the results loaded back into our interface. And then we can see the legend for our data, the parameters, and we can download the data with the parameters, and so that can be visualized, for example, using QGIS or some other GIS software. I think I ran out of time, so I thank you for your attention. And here are the references for the resources you can find online about this project. I want to acknowledge the help from the development team of this project, and also, I mean, the Nrmaps project, which is funded by the European Union, and then the data providers. And thank you for your attention. If you have any question, I'm here.
Thank you, Giuseppe, for the presentation. He forgot to mention that he got the best poster award for the CISBAT conference for his heat-learn that he presented today. So we have time for 2 short questions or 1 long question. Do we have a question in the room? Okay, it can be a long question. Yes, okay.
Hello, so it's me again, sorry. I wanted to ask, you said that you trained only on Geneva. Did you make any effort? So you trained, I think, with some climate variables, but how do you assure that on the climate side it's also applicable to the rest of Europe? So
yeah, no, that's a good question. We don't. So basically, when you apply the model also online on their areas, you have a disclaimer that I mean, we trained the model in Geneva, and it's a climate-adapted data set. So they use the heating degree days to normalize their data. But of course, yeah, the performance in different climates still might be different, and as also the building types.
So the data is normalized by the heating degree days
Yeah.
and then multiplied again with the heating degree days.
Yeah,
of
yeah, exactly.
Thank you.
Thank you. And I think we have one question online.
Not a honor.
I have to take it for once we have one question online.
Okay, so finally there is one. Kevin Mather is asking, has it been evaluated on real work data after deployment?
I mean, we trained and tested our model on real data from Geneva, but as yeah, it was not validating on other datasets from other countries because yeah, the best of my knowledge, it's very difficult to find this kind of data available. So of course, it might be confidential data, but we wanted to use open data as the source. So.
Thank you very much, Giuseppe. I think we can also give him a round of applause. And I'll give the floor to René for the next presentation.
Okay, thank you. Again, I'm not giving the presentation, don't worry, I'm just the moderator. So we now, when I came here this morning, I looked at the program and I saw there's a lot of forecasting in this program. And well, that's probably because it's one of the obvious choices to forecast and visualize demand or supply. And so we're not the first guys coming up with this. So now we go in the history of it. And I have now two folks, I've been informed, that gives so the first presentation with two presenters on stage.
Yeah.
At the same time or sequentially?
At the same time.
Okay, okay. So we make it a bit crowded here. So Doms, I give you and Jerome just the mic. So no, not the mic, but
this one.
This one, yeah. Okay.
One each.
One each.
One each. Hello. Can you hear me? Cool. Yeah, so hello everybody. So I'm Dominique Genoux from HESSO. So as you can see, I'm an old boy now. So I'm here since a long time. And the thing is that we have a lab in at HESSO that is doing a lot of different machine learning stuff. And so I will not talk about that in details, but my trajectory comes from IDIAP a long time ago. And we were experimenting neural networks at that time. So we are still using them for many different things, and we use a lot of different algorithms too. And during the years where I worked there, we also have started up many different startups. So the idea is to be between research and application all the time. And that's why today I will just go a bit more global. So everybody talked about details and detailed research. Jérôme is there for talking about that, but very quickly at the end. And what I wanted to propose you today is just the history of what we did here and why we did it. And everything started 10 years ago, so 11 years ago in 2010 in Brussels when the IEEE organized a conference about energy, smart grids, electricity, and I thought this starting point was very interesting because they were, trying to anticipate and forecast what will be the world in 10, 20 years after that. And so the idea was how to put some concepts on what were the electricity grid at that time, and of course the energy that goes with that. And many of the concepts that were evoked at that time are now, you start to apply them, and companies and utilities are starting to use them and understand them. It's more difficult than we thought, but still it's very interesting because we had virtual power plants, we have microgrids, we have all these kind of concepts. And at that time in Valais, not many people were talking about that, that even didn't know about that. So the thing was, how can we, we are a big producer of energy. We do have different utilities companies. So how was it possible to mix the two? And so for me, the thing was interesting when, I'm a computer scientist, so that's the place where data are that are interesting me. And the main starting point was there to try to think about where do you produce the more data. And where you produce the more data is what we call microgrid, the place where you do consume things, you do produce things. If you use, solar panels or things like that, and you try to store things. And so that's the place where you have the most data, so you can do something and then apply our all magnific algorithm that we have. And so the idea was really fun, and we did start, in 2010 with this IEEE thing, and we started to have different kind of projects, so to interest people at different level, and we did start with HSSO at that time with people that were, so I am in the business schools part because informatics is there, but also a lot of engineers were interested in, and Pierre is one of them, and he will talk about that later. He's now the head of the Institute of Energy and Environment. So everything progressed there. So there was, technical things, research things, there were structural things that just grew up in Valais, and that's very interesting. And also the last step was how to interest the people that were the most important there, which were the people who were producing data or who were using this data after that. And so we started many years ago with little projects, and these projects, so we did do some research to improve what we had as models, as understanding of how energy systems works, like modeling. I've seen today like modeling houses, but also modeling the behavior of users, and also modeling electricity consumption and production. And so we did try these kind of things. And so the idea was just really to keep in touch with the research and to be able to translate in applications after that. And so we started with collecting data on our own environment, which was fun because we had to convince people locally that we wanted to collect data to be able to have something to, as you know, for our models, we need data. And so they were reluctant at the beginning. So they were really, it's useless. We'll never be able to do predictions, something like that. But some of them say, okay, you're local. So and we say, yeah, we do install things. Please just check it that it works. And so what we did, and after the first or second iteration there, then we started to have some tracks. Everybody's starting to work on this, and now we are 10 years, 11 years after that, and we still have, we have a good traction, and so they are taking us more or less seriously now. I say more or less because sometimes more, sometimes less. But so they see they start to see the reality, the thing they can do with us, and we do have now a lot of implementation that are all over Switzerland, I would say. And it's crucial because, as you know, and as you do, we need data, and we need reliable data to be able to train our models and do things that are useful. And so that was all this work below that. And as you can see, we had projects in different levels, from very practical projects that were just taking care of data and taking care of very small things, very applied to European projects or research projects. And so, of course, many people now start to work on that. And if I come from so I just talk about the Institute of Informatics. So we have now 3 different labs that are working more or less on energy, some more, some less. You have here the heads of this lab. So yeah, there's David Vanier, there's our presenter from before, René Schumann. And
So that is the mechanic on our side, but what is also very interesting is that we are connected now with the engineering part. I have to apologize because I forgot the second part of our domain, which is the economical program. Amin talked about that just right before. So there's also people coming from the economical part, but we have Stéphane Genoux, that is a guy that is also an engineer, so we are mixing knowledge there. But what was very interesting there is that, in fact, we were able to create, these are internal stuff for the ones that are not at HESSO, but we were able to create a new interdomain institute that was collecting all the knowledge that we had. And so we have Pierre that will talk this afternoon, and it is the head of this interdomain institute. And I think this is a really, really interesting thing, because to be able to make our work efficient and useful, we need to have all these components. So we don't need only research parameters, the highest level of models you can have, but you also have to implement them, and you also have to collect information. You have to create the information system that goes with that. And so it's a multi-knowledge system. And so what we had, and I've seen this morning, I think we will see this later, we had to collect a lot of different kind of data, and data are still crucial. And but what kind of data, what level of data, what quantity is very important. And then so we did collect things like sensor outputs, which are really the basics of it, but also of course production, storage, consumption, but also things that were pretty important to be able to set up and train our models properly were also, we have seen administrative data, geographical data. We have seen just before that they are really useful, but also the weather. We also have seen this today, but also user behavior. So we had a European project there, and yeah, it's okay. And all this mix. So we were able to experiment a lot of different kind of machine learning models, from Gaussian mixture to the decision tree, random forest, and of course neural networks. And then I will just let Jérôme talk about one of the little things we are doing now, which are just continuing this general work that we have done until today. And just one thing maybe that is interesting is that we are used to use different kind of models, and when you have to manipulate a lot of data, then we need this kind of things and approach that I will let Jérôme now explain.
So hello everyone. I will do it really quickly. So the idea, we are working a lot on the images, and it's a similar issues than with the energy. We have a lot of data. So we use deep neural networks, which are really good. They are very efficient when you have large data sets, but you need a lot of data to be trained, and it takes a long time. Then you have decision tree ensemble, like for random forest, we are very efficient. They have a fast convergence, and they are very efficient on small data sets. So the idea that we can implement as well, and we are starting to implement for the energy dataset, is the combination of the two different types of machine learning. The idea is to use decision tree ensemble to select the different features, so we can train deep neural networks with less input features, so everything will be reduced, and so you can train it really faster than with the original data set. You can use it as well at the end, for example, to do false positive reduction. So you take the output of the neural networks, and then you just select the final output. These things is implemented for images, but we are starting to implement for the energy, and it's really interesting for the current project. Thank you very much. If you have any question.
So as you see, the good news about when you have like research, the old guys can't say in earlier days everything was better. That's absolutely not the case. So, questions? Yes. Don't hold back, because yes, I know it's coffee break soon.
It's coffee break, very important.
Yeah.
You will have coffee break
Anyone
after
has
the questions.
a question before, brave enough to ask a question before the coffee break? You want me to do it, right? Okay, one question. So, you now look back at 10 years, and data collection is and was the big thing. Where are we in 10 years?
What do you mean about data collection?
No, in general. I mean, today I just mentioned, there's a lot on prediction, and the prediction started, as you pointed out, as in data collecting things. Now, in 10 years?
In 10 years, we made multiple loops, in fact, and we are now figuring out that our prediction works. But they are working locally. So, I mean, we had to collect a lot of local data, so it should work there. And the problem is generalization. And I think it's the next challenge there is to be able to train more or less local things that you can generalize after that. And that's why we have to involve all these utility companies, because they have the potential to do that. So to go from local research, local places where you can do very nice predictions to something that is much simpler and much more general, and that you can deploy on hundreds of thousands of households or large network.
Okay, thank you. And with this, one last question. So everyone now needs coffee, so let's go for the coffee break. And we are half an hour coffee break? Half an hour? Yes, okay.
Cool.
So
enjoy your coffee break.
It's one of the objectives of the workshop is to network. So,
Right. We will start again. Thank you. So I hope you enjoyed the coffee break. So we'll start again now with 4 presentations just before the lunch break. Again, a break, but you know, communication is very important in the workshops. So I would like now to introduce Marco Tognoli, our next presenter, who is from Politecnico, not di Torino this time, but from the other in Milano. And he's going to talk about some fuel-saving potential simulation and estimation when, and the title is too long, so I'll leave him the floor right now.
I like the long titles. I mean, it's a defect. So hello everybody, I'm Marco Tognoli. I'm a PhD student and currently terminating my PhD studies. And today I'm going to present yet again a work based on a district heating network and particularly on an integrated framework modeling either the demand sides and the supply sides. So this is motivated by also the recent news that we heard a lot by the goals of the, for instance, for the Paris Agreement and also the recent ones of the climate change conference by the United States and their goals are reducing the footprint and particularly also the primary introducing some primary energy savings in those particular systems. So while the demand side is still fixed in some scenarios, a lot of potential can be highlighted by the generation sides, and particularly in the context of in the industrial. And today I will talk about the residential and commercial applications. The fire-tube boilers are generally simple devices which are integrated in those systems in order to provide the demand. And generally, in this case, we're talking about hot water boilers. And back on the topic that I was describing regarding primary energy savings and their energy savings intervention, these are generally have 2 main drawbacks, which are those interventions are traditionally made, which are that they need huge capital interventions and also technical difficulties during those interventions. So a novel approach in this sense is represented by implementing much optimized control strategies, particularly in the supply side, which is bounded to the prediction of the heat demand of this district heating system. And this is in contrast with the current control strategies, which and we see on the left part of the screen a representation of a climatic curve control strategy in which these are not, do not describe the dynamic effects of this system. So in this study, the Politecnico di Milano Leonardo campus has been selected as the district heating network. And this is composed, is a medium-sized district heating network. And I also, this is composed of 22 separate buildings, which are connected by 2 distribution loops, and as we can see on the left part, on the right part of the screen, and within a single power plant. And those system is monitored, particularly with respect to the thermal property, the thermal variables, but also we have additional information regarding the environmental, solar irradiance, and the electrical loads. And the key data of this case study is that given the medium to large size of this system, which covers more than 100,000 square meters of heated surfaces, and we have enough information to draw the thermal energy balance of each subsystem separately, and the seasonal fuel cost of the current seasonal fuel cost, given the average price. We're not mentioning the actual prices of natural gas is around of 1.6 million euro per year. So that within this information, we can then define the 2 main objectives in the system. So basically on this preliminary data analysis. So we have a potential in reducing the thermal losses of the distribution network, while also as the second objectives has been highlighted that there are excessive thermal generation events which are caused by a mismatch within the current control strategy between the demand side and the supply. So these two main activities, which are then the first one related to the modeling of each subsystem separately, then can be combined together, all these models, in order to provide a simulation environment for the optimization phase. So data-driven modeling approach here is used since we have no information regarding the geometry and the technical data present. We just have this information of the primary and secondary loop of the system, while this methodology allows to also include the dynamic thermal behavior, so in contrast with the traditional control strategy. And we'll also investigate the effects of the lag in the system, which is caused by the injection, the timeline between the injection point and the extraction point in the system. And given the limited control horizon of the optimal controller, a short-term models ranging from 15 minutes to up to 1 hour ahead will be considered. So in this scheme, the overall first part of the investigation can be seen, particularly in the orange box. We see the development of the data-driven predictive models of the thermal performances of each single subsystem. So ranging from the secondary side of the buildings down to the generation side. So we model basically all the elements present from the buildings, distribution side, and the generation side. And the second dimension of investigation is that different machine learning models have been included in order to then estimate the resulting accuracy of these models. And finally, the third dimension of investigation is represented by the prediction horizon. So we have different models within a variable prediction horizon range from 15 minutes up to 1 hour ahead. And another important step is represented by the feature selection. So after the training phase of these separate models, which are then also foresee the implementation of a genetic programming-based pipeline optimization algorithm, the feature selection serves as two main objectives. The first one is the reduction of the feature, so based on the estimation of the feature importance with respect to the dependent variable, and also gaining some explicability. So today we talk about making the models generalizable, and this is an important step in order to achieve at least partially this goal. So that after that, when the set of features, the just important set of features is selected, another training phase is then included. These models, it is worth highlighting that they can be combined together in order to provide the overall estimation of the system. And these key results, which are based on the training phase of implementing a chronological approach, either from the training and testing and also the validation phase, foresee for instance, for the distribution side, that given the limited time frame, there is no much dependence over the external features. So that's since those phenomena has a much more wider time horizon, while there is a notable importance by the supply temperature conditions. And the achieved score are always lower following this methodology, lower than 6.5% as the mean absolute relative deviation. And following the feature selection step, so after selecting the set of features, we see that also there is a remarkable reduction of the model's error, then an improvement of the prediction capabilities of the models, with compared to the previous slide, even in the worst case scenario. And as predicted, higher the prediction horizon, higher will be the error of the model, so ranging from 15 minutes up until 60 minutes. And regarding the estimation of the time lag introduced by the dimension of the distribution network in the system, so between the power plant and the furthest building in the system, there is a 15-minute time lag, which is measured by the difference in step between two injection moments of the temperature measured, and that can be highlighted in this scheme by the superposition of the two peaks. And finally, all these models are then combined together in order to first retain the granularity, but also to provide the overall estimation of the thermal performances of the system, such that they can be serve as the control basis of the constraint optimization that we can see here below, which is subject to the minimization of the return temperature towards the power plant. So this allows thus a reduction of the thermal losses on the distribution network, while it is constrained by the thermal demand, the predicted thermal demand of the system. So in order not to encourage any discomfort. And the preliminary results that has been also extended to a wider set of buildings have highlighted that there is a potential of reduction of this of the fuel cost by 4%, which in this scenario, given the fuel cost of the system, equates to nearly 65,000 euros. So it is a notable energy saving. That it is also worth highlighting again that it requires a marginal investment costs, and also the intervention times are really lower compared to traditional energy savings intervention. And in order, I'm going forward to the conclusion part since my time is almost up. Here in this investigation, it has been proposed a framework, a generalized framework for modeling the overall district heating network while still retaining all the granular details, which can then be used also for further studies, which of course are not the subject of this presentation. And it's also worth highlighting that not only the thermal data are used, but also data sourcing from the fields, ranging again from the electrical and external loads. Comparing different type of machine learning architecture allowed to select the most promising technology, and the implementation of the supply, the optimized supply control strategy allowed a reduction of nearly 65,000 euro per year, which is like free money in this sense, given the limited investment costs of this activity. The study has to be concluded and also validated on a wider set of case studies. So this is thanks to a collaboration with the Didier Research Institute, so that in order to provide a more generalizable approach of this methodological framework, while a sensitivity analysis is going to be investigated with respect to the control horizon of the optimized controller. So this sum up all the activity of today. So I will also thank you for your attention.
So thank you, Marco, for the presentation.
Thank you.
Do we have any question in the room? Yes?
So thank you for the talk. You had 2-3 things in which you have these subsystems where kind of different things go in. So you have this control strategy, you have the forecast. Could you, or did some kind of analysis on, like, okay, where the improvement comes from? Is it from the better forecasting? Is it from the better control? I mean, could you isolate the effects?
So the improvements is kindly related to the, instead of the reduction, as we can see on the graph, there is a generalized reduction of the peaks of the thermal demands with respect to the traditional control strategy. So this is strictly connected to most probably to the control sides, rather than and this is helped also by the forecast. So I mean, the answer is there is a combined effect over this phenomena. So most generally, yeah, it is a combined effect.
Just a question, like, could you test traditional control with new optimum forecast and vice versa things? So.
Yeah, exactly.
Any other question? No other question? So I think we can give him also again a big round of applause.
Thank you.
And I'll give the word to René for the next speaker.
Yeah, so it's a bit like microphone ping pong here. Sorry for that. Okay, we go for the next presentation, and the presenters. I heard it's 2 again, so somehow this seems to be a pattern when I have to moderate. Yeah, you know, I had a good bargain here. So while they say set up, so we now go for the another part of complexity by changing parts in the sense of something can move. So we go now to the mobility, and these things also need to be fueled, and that's yours.
Thank you very much. Il n'y a toujours pas le double clic. Et puis après, c'est où le mode présentateur, c'est ça? Attends, il démarre. Non, je sais. Tip top, merci beaucoup. Okay. Thank you very much for the invitation. So today I will present the project called EVIP for Energy Visualization, Integration and Prediction. The base idea took place in Val-d'Airain. Several hotels wanted to promote the image of a green and ecological region through the green mobility concept. They received the award Best Innovation in Services in addition to accommodation, and that was the first discussions. We have built our development infrastructure at Technopole Sierre and worked with Bachelor thesis to create the first proof of concept. After the first phase, we needed to improve the charging station capabilities. We added a UniPi to have full control on the power and the energy meter to collect the data. You can see here. We had the chance to improve the hardware and software on our real test infrastructure at Campus Bellevue-Sierre. The new versions are continuously tested by professors who are teaching in business IT course program. Idea of the EVIP project was to help directors and managers to understand the energy flow in their hotels, especially if they add EV charging stations. We use machine learning algorithm to predict the available power regarding own consumption and eventually local photovoltaic production. We based the VIP architecture on the Edge 2020 GoFlex infrastructure to collect data consumption and production, and we added the machine learning server to predict the available power for the EV charging stations. The project Digitalization SCCR Furies complements the EVIP with user interaction. We need to add information to our machine learning algorithm, as AC charging stations do not allow to get information from the vehicle. We need to ask battery states, time to departure, to better predict the available power at the hotel. To interact with end users, we implemented Android and iOS apps to collect the information and also display the actual status of the charging station. We can easily understand the red part, charging in progress, the green where the EV charging station is available, and the orange one, this one, is one of the most important status for us, is the vehicle to grid availability. It means the car is full charge or charge like the parameters and is available for concepts like you have heard certainly about vehicle to grid, vehicle to home, vehicle for grid, and that will be the next services we will build on that. We have here a representation of the energy flows from the grid of photovoltaic power plants to the charging station. In parallel, you can see the data flow from hotel to time series database for the consumption data, and flow to manage the EV charging station through UniPi. I will now give the floor to Jean-Marie, who will describe the implemented machine learning algorithm.
Thank you, David. So yeah, just a quick introduction. I'm Jean-Marie Helder. I work as an assistant at the HSSO with David's team. And so today I'm just going to talk a little bit about the prediction we implemented for the EVIP project. So our main goal was to predict the available power for hotels in the next hour period. So we based our work on Luc Dufour's thesis, who was introduced by Dominique and Jérôme just before, especially his ISAC 2018 paper publication. And he presented a machine learning method that tries to predict energy consumption for a microgrid and also for a restaurant. And he used data like time data, production planning data, and weather data to predict it. And he both presented a classification method and a regression method. So for the classification method, several algorithms have been tested. And the one that came out to be the best is the gradient boosted tree with an accuracy of 98%. And it's good to note that the classification problem we had, we separated the results into 6 different clusters, which represented 6 different levels of prediction, consumption prediction. Yeah. Here we also have the results for the linear, for the regression problem. And once again, the gradient boosted tree came out to be the best method with a coefficient of determination of 0.98. And just below it, we can see the graph of the consumption over a 30-day period. Within red, the measured consumption for a restaurant this time, and in blue, the prediction. So we can see that the results are quite promising, and all the power peaks have been discovered. It looks like the results are promising. So what did we do with them? We implemented them on the EV project to try to predict the consumption and also to try to predict the available power in order to use as much as possible self-produced photovoltaic energies. So here we created a simple and user-friendly dashboard where we can see the energy flow of the hotel, starting on the left with the photovoltaic power produced going into the hotel and then being used by the charging stations. And on the next tab, here we can manage our charging station and its states. For instance, we can set it on or off. But what is most interesting for us today is the consumption prediction on the bottom right. So instead of having 6 clusters, at the moment we only have 4, and we change them into colors, the green color represents low consumption prediction, so high availability, and red means the opposite. And with this, and we can also set the management method of the charging station to automatic on the bottom right. And if we do this, the amps of the charging station will set according to the consumption prediction. And like this, we ensure that as much self-produced photovoltaic energy is used, and also all the other hotels' installations can use the self-produced photovoltaic energy. So we've seen that we've seen a lot of promising results, and we have also shown that we could implement a real-scale system and architecture with the hotels participating in the study. But we've also seen some challenges. For instance, how complex it was to define an architecture with so many different stakeholders, so many different systems and technologies. We also had to deal with a maximum power limit for each hotel, which was due to the GoFlex Cloud I/O gateway used to gather
electric data. And for instance, one of our hotel was higher than this consumption. We also had to deal with some deferral, with some delays. Of course, installation delays means software installation delays as well. And of course, we don't really think about it when we're working it on the lab, because we also have to deal with external problems like IT problems, network problems with the hotels. And I will let David for the final words.
Thank you very much. Our goal at University of Applied Science is to disseminate at different levels. So we participated to the local public event 15 years, the ARC Foundation. 600 students visited our presentation here. We also co-organized the Climate Emergency Day with students from Lycée Collège de la Planta. It was here, the presentation of the whole concept. We had the chance at the national level to join the Swiss Competence Center in Energy Research, FURI's digitalization project, and also present the result at the National Photovoltaic Conference in June, physically. It was a great chance this year. And at the international level, as mentioned before, the International Sustainability Energy Conference, you can find the references there, and also in the MTBI journal Energies. Just about EasyLab, our goal is to easily integrate new technologies to help and accelerate the energy transition. We are working on 3 pillars: visualization with the GIS. So we co-developed with the CREM the Edge 2020 hot maps based toolbox, and the blockchain or decentralized systems integration is the second pillar. The third one is DevSecOps to integrate security in the development life cycle. Thank you very much. I think we are on time for the questions.
Okay, thank you very much for your presentation. So, questions? Take a look there, good. I have one. I have to admit, I am not particularly an expert in running hotels. I mean, yeah, you probably have here some guys who know it, but I don't. So if you explain to these hotel owners, I mean, why is it not just buying, installing, and done? I mean, why more?
The idea is just to anticipate the evolution of electric vehicle popularity. If we don't anticipate that, they put, for example, 10 EV charging stations, 11 kilowatts, it means the hotel will have some troubles, depending on what you are cooking at midday. So the idea is to help them and to help them to do that right and to understand the flow.
Okay, thank you. So we are 5 seconds on time, so wonderful.
Thank you very much.
So thank you again for your presentation. So we'll go now to the next speaker, who is getting ready here. So we have Dr. Javan Rudy from EPFL, from the Solar Energy and Building Physics Laboratory. So he's a postdoc there with Professor Scartesini, and he's going to talk today about energy hubs and sector coupling.
Yeah, and spatial coupling, actually.
Sector and spatial coupling.
Yeah. Thank you very much. I'm Calvin John Rudy from LESO. And today, I think for the next 15 minutes, I'm not talking about prediction and technically machine learning for now. And I'm going to present our proposed concept, Urban Cell, which is focused on enabling sector and spatial coupling in design optimization of energy system and benefits. So why we need sector coupling? So we know that we need to reduce greenhouse gas emissions by more than 80 to 95% compared to 1990 levels in European countries. And for doing that, we need to decarbonize the European energy system. And of course, so we need to improve the efficiency and flexibility of energy system prior when we're going to design those. And main challenge is reducing the cost of decarbonization actually here. So what we can do is focusing on 4 major sectors inside an urban area, which is energy supply, industry, transport, and of course energy demand from the buildings, and try to reduce that decarbonization cost in those sectors. So sector coupling is technically recognized as the key in the energy transition for future cities. So by interconnecting the energy consuming sector like building, transport, industry within an urban neighborhood, urban district, we can do that. So originally developed in Germany, I think the German word is sector Kupplung, hopefully I'm pronouncing right. And the main concept was to electrify the end use sector. So that was the main focus of sector coupling. And of course, the main definition that we have from EU reports is to provide greater flexibility to energy system and to decarbonize those with cost-effective way. We also have several recent reports and national and international reports concerning sector coupling and of course special coupling, which is technically those interconnectivity between different energy systems in a real urban area. So the state of art in considering spatial and sector coupling, there are several concepts like smart grid. We have energy hub, which is technically an extension to hybrid energy system concept. And of course, the goal of those are to improve the renewable energy integration in urban areas. And we have also other metaphors like in urban systems, like urban metabolism or industrial ecology, which is more holistic. And if you want to summarize the pros and cons for this present concept in this regard, so none of them can both consider sector and spatial coupling at the same time. So smart grid, energy hub, hybrid energy system, mostly focused on energy sector, while urban metabolism concept can consider those but cannot consider system dynamics. And that's a main problem. So it's not specifically designed for urban energy system optimization actually. So we want to go toward spatial and sector coupling. So we presented urban cell concept. So if we consider a city in the A here, we have different districts and different areas. Each of them consider of different neighborhoods, which we call them a cell. And this is one cell in our concept, which of course there are several services and layers in that cell, from energy to building stock to transportation and other sectors. So that's the first step for sector coupling. But of course, we need to go beyond that and consider spatial coupling too. So between each cell, we have also interconnectivity problem, and that we need to consider that in the design optimization of urban energy system. So we try to come up with that concept and try to hopefully consider all of those positive requirements to optimize an energy system. So urban cellular network is technically based on connecting different urban cells in an urban area, could be a district for example, and create a distributed multi-agent design problem. So instead of focusing on one system, we're dealing with system of systems. So most of these studies in design problem, especially in design and control problem, we also have that, but in design problem are focusing on one unit, one energy system, and try to optimize that. But we're dealing with a system of system. So for the operation mode, we're not focusing on control, of course, here, but for operation mode, we propose a leader-follower strategy, which is a technically efficient way to consider interconnectivity between each cell. It's a combination of like fully cooperative and non-cooperative, which each of them has some negative points. For example, in fully cooperative operation mode, we have a central authority intervention, which for sure can lead to a more efficient energy system, but we have privacy issues there. In non-cooperative, so we have some agents that compete with each other, and of course we have a good privacy there, but sometimes we'll have problem in having optimized and more efficient energy systems. I'm trying to very fast talk about the optimization framework. We have a two-level optimization. Here, at the first step, we're going to looking into the optimal and co-optimization of urban energy system and urban morphology, and of course the transportation sector that we consider. And based on this optimization workflow. And then, of course, here we use like most heuristic algorithms to optimize our problem, considering the complexity of the problem. So previously, our team, for example, worked on more, let's say, evolutionary algorithm or machine learning one, like deep reinforcement learning for the dispatch problem. But since this problem was quite complex at this stage, we couldn't use that. And we're focusing on NPV and GI grid integration. So NPV's life cycle of all the costs inside the design distributed energy system that is based on PV panels, wind turbines. We have heat pumps and the dispatchable energy source, of course, to dealing with the mismatch between supply and demand. And we also have the grid integration as a function for our optimization, which dealing with the autonomy of the neighborhood. So at the first step. The second step, we try to organize our Pareto solution from the first step and make them ready for the third step, which is energy network optimization. So each Pareto solution have a unique urban cell, and of course are organized in descending NPV order to be used in the third step. In the third step, we have a two-stage optimization. We optimize the network configuration, connecting the urban cells and their decision vector, and then we compute the flexibility of each line in the network. And finally, we can say that we're optimizing the strength of the network and system configuration, which means designing of the energy system. And the fourth and fifth, let's say, steps are, of course, relevant to the first 1, 2, and 3 step. So they're running iteratively until reaching the like epsilon Nash equilibrium. And then we have optimal urban cell configuration in the fourth step. And finally, optimal network connection using energy internet concept. So we, each cell, we have an interconnected energy infrastructure. So we talk about energy hub, we talk about building stock, we talk about transportation for each cell, which is the neighborhood, and of course, going to have like optimal output for each of them. For the urban morphology model, we're using these three elements, so urban form, function, and structure. So urban form usually, the concept is used instead of urban morphology. Urban form is focusing on geometrical part. And based on these 4 major morphological parameters, and of course, a range of 10 parameters, we developed an urban area consisted of 9 cells, which is cell is a neighborhood, and with different, like it's a multi-function urban area, office building, residential building, low, medium, and high-rise building. We came up with an 1 kilometer in 1 kilometer urban area. We had to design this to have a more control on our problem, so we couldn't use existing, let's say, urban areas. And of course, we, based on the function, based on the occupancy of each building, we developed the model for the transportation and EV charging station to be connected to energy system. And we run, of course, a multi-zone energy simulation for this. So if we go back to that cell concept, technically we're dealing with these 9 cells. So first we try to consider and assess the impact of urban morphology and EV on the hourly resolution. And I'm passing this because I think I'm running out of time. But then we're going to assess the UCN, or urban cellular network impact. So we defined some benchmark scenarios here. So we have fixed generation without sector and interconnectivity or special coupling. We have isolated coupling infrastructure, another scenario, ICI, which only considers sector coupling. And of course, UCN, our concept, which consider both. So if we look at the Pareto solutions, we can see up to 37% reduction in system cost using UCN. And that compared to FGS. But for on the sector coupling model or scenario, ICI, we only have like about 7% reduction of the infrastructure cost. And another impact is to looking into more details. So here we have, if we select 3 P, Q, and R Pareto solutions, which are minimized or minimum NPV for each of this scenario. If you look into that, we see a different configuration for urban morphology. So that shows that urban morphology has a great impact here. And we also can see with a more detailed insight into those solutions, we can see that urban cell can improve the renewable energy potential by 25%, as solution R is from UCN and solution Q is from ICI. And what about the scalability of the proposed approach, whether this can be scaled up to bigger problems? So we did analyze those 3 benchmark scenarios together from 4 cell to 6 cell and considering 9 cells. So we can see from when we're increasing the number of the cells or neighborhoods, we'll see that the ICI and FGS was shrunk, the Pareto solution was shrunk. The reason is that they will need, because there is no connection between each urban system, they will need to have more distributed energy system to actually get the demand of the area, and that will lead to higher cost, of course. But using the NPV, of course, we'll have like 25% less NPV reduction. And finally, what about this impact of system architecture? So we have a game theoretic approach to assess that. So we have ICI, sector coupling, and we have game 1 and game 2, which are 2 consecutive games in the optimization problem. And finally, UCN, which is the 20th iteration of the games. Here we see that in the first and 2 game, the UCN concept somehow coincide with the ICI scenario, which only considers sector coupling. But after the 3rd iteration, it will be more similar to what we see here, which is the 20th generation, and a great reduction in NPV, and of course lower grid integration level, which lead to higher neighborhood autonomy. So if we summarize the main findings, we know that we have the problem, we know that we should consider sector spatial coupling, and this concept showed us that cost of interconnected infrastructure can be reduced by 37%, and renewable energy penetration can be improved by 25%. There are some ongoing work based on this concept, so we need to use and add more uncertainty sources. So what about climate uncertainty, climate change, extreme event, microclimate condition? All of those could be important in our model. And of course, demand response management. So instead of focusing on aggregated data of one neighborhood, what about considering all buildings as an agent and move toward a multi-agent optimization problem? So we done some work in that regard for like 38 European cities concerned to climate change. We saw great impact, especially for the cooling demand in future, and those are something that should be considered in future. And climate resilient interconnected infrastructure, we should improve the resiliency of urban energy system to the climate and extreme events. And so we also done some work in that regard with the same team, but this is something that should be added to the urban cell concept and analyzing it, because there we only use a TMY file and a mode file based on energy balance equation, which lead us to the other problem, which is microclimate data. We worked on that also, and we realized that there are some major problem, and microclimate impact on UBM, urban building energy model, is up to 35%, and it can be even here in extreme events. Problem is for annual scale analysis, we usually use urban building energy equations, balance equations, but we need more accurate predictions. So of course we have under review work, which we developed a hybrid model based on CFD and deep neural network to predict microclimate data on annual scale using CFDs, which I think that could also be another source that could be added. And finally, of course, moving from gray box to black box modeling and going to that demand response management. This is for 1 unit of energy system. Our team actually did some analysis using deep reinforcement learning, and find out like improvement by 60%. That's something we couldn't do it for our concept now because it was too complex, to be honest, to do that. And but we're working on that. We're going to that direction. I'm sorry to mismanaging a little bit of time, and thank you very much for your attention.
So thank you, Kevin, for a very nice presentation.
Thank you very much.
I think we have time just for one question. Do we have a question in the room? Yes.
Yeah, thank you for your presentation. So your urban cells, can you have multiple layers of your cells?
Yes.
Okay. So now, can you, because as far as I've understood, you have different, so there's an optimization you can have with some number of cells.
Mm-hmm.
So can you have different layers or just keep the optimization?
So that's the thing. So we have, that's sector coupling. So we have different services inside the cell, which let's say it's like, let's say that it's like a neighborhood. It's a building, it's an energy system, or transportation, industry, anything. So that's sector coupling. We had some work on that, of course, and some concept doing that, as I try to present it very fast. But another thing is interconnectivity between those. So that's the major problem also. So that concept, urban cell concept, is trying to consider both at the same time. So each cell have its own energy system, but of course, there should be some connection between them, some interconnectivity to let's say, solve that mismatch between supply and demand. Of course, keeping the privacy. So we don't share all the data, of course. So it's like grid injection, purchase rates. Only those data could be, at the same time, be shared between those different urban cells. So at the same time, you have sector coupling at each cell and special coupling between each, let's say, urban cell or neighborhood. So a combination of several neighborhoods, a district, for example.
So thank you again.
Thank you very much.
He deserves another round of applause.
Thank you very much.
And for the last presentation of this morning, I will give the floor again to René.
Okay, we kind of now start from the sector coupling from the big setup to the operational world on flexibility. And so on this forecasting, it's not on supply and demand, but it's kind of the first deviation of it. You know, so you just have to derive your functions, and then you get flexibility. And now Pierre-Rudy has the stage for telling us how to predict these.
Yeah. So thank you for the possibility to give a talk here. I just want to present a bit what we are doing on the flexibility of households. That's the work of multiple persons already also in the room. So perhaps for some of the questions, they are more able than me to answer. But let's go to the stuff. We are working mainly on the basis of two European projects. So that's GoFlex and Domaris project, where we deploy an IoT infrastructure in about 200 households and other elements, but mainly I will focus on this household today. We implemented demand-side management in this household to be able to control the heating appliances, mainly cutting off heat pumps, because most of the households that were in the project were quite recent villas with heat pumps. But the idea is also to prototype other kind of services such as analysis of the heating performance, or I don't know what, analysis of the consumption to give advices to the client. If you look to what was done, you see more or less part of the installation here with the smart meter, what we call a smart meter, a gateway just next to it connected to an optical line. And then you have also on the right Ripple control infrastructure that we were hacking to be able to connect, to act on the heat pump. And we had multiple sensors, different wireless sensors that were added to be able to have an independent measurement of the heat pumps or other appliances, as well as temperature of the room, temperature of the domestic hot water, and so on. All this data is collected at something like 5-second wait, 5-second period, with a few watts of precision, so it's quite a lot of data. So we are bathing in data. The first thing that we are, when we want to go into flexibility, is to talk about two types of flexibility you can achieve. So you can try to increase the power of the heat pumps. With the ripple control, is not so easy because you can just shut it down. That means you can decrease the consumption. You could try to use the rebound effect. We'll talk about that afterwards. So what we wanted to have is to have a prediction of the load curve. So we work on the data of this more or less 200 households, a bit less than that. And you have here a heat map giving you the power, as average power per household. You have on the left the global load curve, and you can see what is quite logical. This kind of line at midday and a huge line in the evening, and you have the influence of heating in the morning and the evening, mainly in the winter season. That is appearing. And you have the global load curve, or the load curve without the heat pump, without the heating, more or less, where it's reduced. And if you want to go to the what we can control, so predicting the flexibility that we have and where we are able to use, you have these two heat maps that were produced based on the energy used for domestic hot water production and also for the space heating. And what you get on the side is not really a surprise. So heating is not really performed in the summer, a bit, yes, but mainly in the morning, in the evening. And for the domestic hot water, it's a bit more stable during the year, but still you use it a bit more during the winter. And you have nothing during the night, a bit more, quite a lot in the morning, a bit in the evening, and so on. So if you want to go to the negative flexibility, cutting these heat pumps, you want to just go first to what are the parameters you should use to be able to predict the loads. And the first one that is quite logical is that heating is inversely correlated to outdoor temperature. It's not really a surprise. And what you see is domestic hot water during the year is much more stable. But that gives you also what is the energy you have at your disposition, at your disposal to act on the grid. One of the things we wanted to go was about what kind of model we want to have, because if you are talking about DSM for big buildings, most of the time you are making a physical model and trying to model your building, model windows, model everything to be able to know how much energy you can store or not. For smaller households, it's extremely complicated to get all the information about that, and we wanted to have a look about what is the influence of pooling the households. So mainly, what we just show here is a 180 building, and when we are working with pools, a pool of one household is not really something, but if we are pooling it in a group of 2 households, 4 households, 9 households, 18 households, and so on, that will give you more or less the histogram of the average power per household that you get. And it's not really a surprise, but if you increase the number of the pool, you will have more a normal distribution. And what you can see is that if we go in that direction, starting from a pool for 30 to 50 households, we are coming close to the lower limit where the pools are quite interesting, are quite fitting to a normal distribution. So we worked then after that more on pools, because predicting an household consumption is something, consumption of energy, but predicting when the heat pump really will start or not start is extremely complicated, especially for small buildings. But in a pool, it's starting to be more interesting. If you look to the data on the negative flexibility, so cutting the loads, we used different parameters for predicting it, path values of the load curve. We are also using meteorological features like temperature and radiation, time features, because there is still quite an heavily influence of all the people behave in the households, and also other things like holidays, school or public holidays. If you have a look to the graph here on the right between radiation, temperature, and heating, you can see also that you have some discrepancy. What I will call discrepancy is, as an example, in the evening, when the radiation just starts, you have an abrupt decrease of the heating. It's quite logical. Heat comes in the building, you cut the sensors, you cut the heating solution directly. But when the sun just go off, it waits quite a long time before the heating solution is rising, and you have this kind of first peak of synchronization of the heat pumps that just go off after they are eaten a part of the building, and we go off. So it's not really directly related. You have this kind of delay of the whole thermal distribution system from the heat pumps that have quite an influence also on the system. So we tested quite a lot of models. Constant model is perhaps the easiest one. Linear regression, random forest, multi-layer perceptron, light GBM, XBoost or IMAX, just to test a different kind of model and to see how much we could achieve a prediction. I will not say that's the best model we could achieve. We could all go better than that, but that was the first try. And here you have the S-curve, the prediction of the load. That was quite good if you go for half an hour, 45 minutes is still okay. But you see that if you are going to 5 hours, yeah, the prediction is really falling. Still, LGBM was the best model in the case, and here I can give you a curve of the predicted values at 5 hours or 15 minutes. So 15 minutes, the prediction is really good. 5 hours, you still have a clue, but it's not perfect. But let's go to another field. Not negative flexibility. Negative flexibility is quite easy. It's predicting the load curve of the heat pump. No, it's what could we achieve if we are making cuts to produce a positive flexibility, an increase of consumption. So we worked on the rebounding effect of heat pumps as a positive flexibility, a positive consumption. And the main causes of this peak after the end of the cut is mainly caused by synchronization of the heat pumps and also compensation of the energy that was not used during the cut. It's extremely tedious to get data on real cuts because that means that if you want to have data for every hour of the day, every hour or every month, every type of weeks and holidays, that means that you have to make cuts, and having cuts that have not influence on the next cut and so on is quite awful. That means a lot of data collection. That means that we try first to analyze it with simulation, trying to first simulate the synchronization impact. So the fact that if you are making a cut, you will achieve a synchronization of some heat pumps that will start all at the same time, producing this peak. What we did is just use the standard load curve and just shift the heat pump as if they had been synchronized by a cut. So you push the heat pump that normally had started during the cut to the end of the cut. That means that you are not compensating for the lost energy, but still you are making this synchronization, having an analysis of the data. We did that for the whole year, and we did also principal component analysis based on the curve. I see. And having a look about the synchronization. What you see with the two first components of the PCA, you have the first component that is really being higher or lower, or you can now also have a component that is rising or falling. This kind of two direction is quite easy to understand. The first one is mainly between summer and winter. If you are in the winter, as the load is higher, normally after the cut, you will remain higher. In the summer, if you synchronize of the heat pump, you will have more or less no consumption afterwards. So that's the first dimension of the PCA. If you go to the second one, it's more based on time of the day. In the morning, as most of the heat pump will just shut down or reduce their consumption, that means that that's logical that even if you are making a synchronization, there will be a reduction of the consumption afterwards. Or if you are close to the end of the afternoon, it will go in the other way around and go to an increase. So what we did in the end is to have two parameters that were average consumption before the cut and also time of the day. And here you have this kind of median and quartile of all the data that were collected with simulation for all the year. And it's becoming to fit quite well. That means that 50% are in this, 50% of the curves of the year are between these two areas. So that means that you are able to be quite good. Still, we have to learn a model to be able to do something, but for first analysis, it was already something. And perhaps what we did finally is also to compare that to real cuts. The problem is we were making cuts on 10 heat pumps. And if you make a cut of 10 heat pumps for 2 hours, that does not mean that 10 heat pumps are impacted. So we just took the ones that were impacted and were cut, and to make a comparison with that. And we see that the form of decreasing is quite okay, but there is already quite a big influence here. That is just that when you synchronize after a cut, most of the time the heat pump will go to domestic hot water production. That means that you have an increase of the power because you have an higher consumption for producing hot water as what you do with a flow of water that is going to the building of 30, 35 degrees. But still, that was the first step. We still have to work on that and go there. So to conclude, prediction of the load curve of heat pumps is quite good on my side. It gives you a good evaluation of the flexibility that you have in a household if you pull them with a group of 30, 50 households. We work on the positive flexibility, so this kind of using the rebounding effect and using the average power before the cut and how the day seems to be efficient to get something. It will be nice to have more cuts to compare the simulation and the reality and yeah, see the differences and achieve to have a better model in the end. I hope it wasn't too long, because I know you are just waiting for the lunch.
Okay, thank you for your interesting talk. So now, is someone brave enough asking questions despite there's food? Well, he's to blame, not me this time. You can blame
me. Thank you for your talk. Just a question about the heat pumps. They are doing heating and hot water at the same time?
No, they cannot. A heat pump.
I mean, the heat pump is
the appliance can do both, but they will never do both at the same time because you are just injecting into the domestic hot water tank, or you are injecting the water into the building. That means that the temperature that you are getting outside at the end of the heat pump is not the same because you will be aiming at something like, I don't know, 45 to 55 for domestic hot water, and the building it will be between 25 and 35.
But yeah, but still, would it make sense to have two models, one for the heating and one for the hot water? Because it's not the same use.
Yes, but what is more important that we did not take into account was more that you have a priority of domestic hot water and the heating. That means that if you make an average like we did here, we were below. Because as soon as you synchronize, the priority will start first, and priority is domestic hot water. So that means that you are going to the higher stage of power, the higher power, just because it's written in the controller of the heat pump that you go first to domestic hot water. So yeah, we should take that into account, and that means that you have a probability to go to domestic hot water needs that is increased with a longer cut, and that means that you have to correct it with that.
Okay, thanks again. And by this, we officially close the presentations and now go for the bonus, extras, and food stuff, which will be detailed.
So just before you rush for the lunch,
J'ai le mic, ouais. Il est allumé? Il est allumé. J'ai déjà testé avec Vincent, ça doit jouer. Vas-y, bien sûr.
Merci. Okay, so we'll start again. I hope you had a nice lunch. So now it's time for the last two bonuses presentations. The first one is from Loïc Puteau from CREM here. Well, he's going to introduce himself and he's going to talk about an open data acquisition tool chain for AI applications.
I hope it works. I see. Okay, perfect. So, thank you, Jerome. Good afternoon, everyone, and welcome to my presentation about our open data toolchain, open data acquisition system. Data acquisition system. First, I'm Loïc Puteau. I work at the CREM in mainly on simulation tool and application systems like the one I will represent to you. First thing, why do we need a data acquisition system in general? For several projects, we need to validate simulation models, or we need live data to regulate buildings or to do things like that. The issue comes when such data is not available, which can be the case because the data doesn't exist or because the data isn't free to use. In that situation, you can do two things: not doing what you were doing, but you can also take measurement and create your own database, which is and you can do this with our acquisition data system. So basically, our acquisition data system can measure and take data for almost every kind of thing that can be measured. But for this presentation, I will present you the weather station that we made out of this system. So we take three main measurements. The first one is the irradiation. So with the sensor BF5, we we take diffuse and total irradiation. The second one is the temperature and humidity sensor. So takes humidity and temperature. And the last one is the wind sensor that gives us the wind speed and the wind direction. All those sensors are connected to our mini PC, which is a Raspberry Pi, and the Raspberry is then connected to the network with a 3G antenna. That's a bit for the hardware. Now a word on the software. In a perfect world, every sensor would communicate with the same protocol, but obviously we are in real life, so we have three sensors and three different protocols that we need to understand and to read in order to take our measurements. The temperature humidity sensor communicate in I²C which is a great protocol because it makes us able to have more than one sensor on the same wire. In fact, all sensor has its own address, and when the computer needs to take measurements, it just has the measurement to the right sensor with the right address. The second one, the Winsonic, so this, this sensor communicates in RS-232. This sensor is simpler. It sends each second a string with his current values. So we need to be able to read those values, process them, and then send them. And the last one, the BF5, is an analogic sensor. It means that we basically measure the voltage that the outputs are giving, of the output, the two outputs. So, and then we convert these voltages to irradiation values. Then that's for this part here. Then the second part is when the Raspberry Pi reads all the data, process all the data, so put them in a defined format, and then the Raspberry Pi send all the data to MQTT server. The MQTT server is a server that allows us to send and receive data on a specific topic, which interests us because each weather station will have its own topic to send the data to. And then very last step, the main server is reading all the data that the weather station are sending and push all those data in a big database that is stored in Kemco server. The next point, I will show you one of our weather stations, the one that is here up on the roof, and then two applications of our already existing weather stations. So the weather station of Martigny. Some things. We are measuring currently the irradiation and the temperature and the humidity of the place. As you can see, this weather station was built to be autonomous, so it has a solar panel with a battery in the box that contains the data logger. The consumption of the station is around 1 watt when it's just taking measurements and sending the data. And it can rise to 15 watt when the BF5 sensor start to hit, because when the temperature goes too down, the sensor need to keep to stay warm. So it's mounted with a little electric heater. One direct use of this station is the lighting regulation in this office, which is, in our cases, Jérôme's office. The IDIAP created and trained an algorithm that was able to predict the luminance on the desk of the worker in function of the sun position and the current irradiation. If the algorithm defines that there is too much light, then it can move the blinds to cut the light, or if there isn't enough light, turn on the electric light and improve the comfort of the worker. The end of this project is, of course, to optimize the electric energy consumption linked to the electric lighting. One other application is an application on the Egutskis project. So basically, the idea of this project is to be able to predict the district heating network consumption in function of meteorological data. So we installed 3 weather stations, so one in Montet, one in Verbier, and one in Sion. The idea is to collect data and then at the end to try to train an algorithm, I guess, to be able to predict when the heating system must be turned on or in advance or not. I wanted to do a live demonstration, but as we are now live on YouTube and the script isn't ready on this computer one, it's a great opportunity for me to invite you to come see us at our showroom just outside of this room. But yeah, I'll finish with this little slide for conclusion. So we built a data acquisition system that is on those examples used to collect meteorological data, but it can also very easily be used to measure acceleration, CO2, pressures, flow. In reality, everything that is easily measurable and measurable. Some examples that for other applications. We are currently monitoring some batteries in electrical scooter, or databases can be used to validate simulation models. So that's it for me. Thank you.
Thank you, Loïc, for your presentation. I think it's the first presentation that is in advance.
Yeah.
Congratulations.
Thank you.
Do we have some questions in the audience for Loïc? Yes?
Thank you for your presentation first. You kind of created this sensoring system. Are there, let me say, any kind of lessons learned that more or less, since data acquisition is something we all have. Unfortunately, it's not like us before what will happen in 10 years, and where I learned data acquisition is not a problem anymore. Mm-hmm. Now it still is. So is there anything, lessons learned you can give us?
Yes.
Things that you worked out?
Yes, for sure. It's the case in almost every situation for person that want to acquire this data. The data logger, so the part of the system that read the data and stock them or send them to the network must really be reliable, because it's really the worst part of the system. I mean, all the sensors will work just fine because they are built in order just to send the data, send string, or to change the voltage in function of the weather, for example. We had some issues with the data logger because we use Raspberry Pi, and it works with SD card. And as we did not know at the beginning, the SD card can very easily be corrupted. And therefore, we had to define that was the problem, first thing, because of course, at the beginning, you're just like, okay, my station isn't working anymore. Why is that? And then you go on place. You just turn off the power and turn it back on, and you say, okay, it runs again. That's a strange thing, and this happens again and again. And then you take the card out, you put it in your computer, and you just look at what is still in there. And in some of your programs, you've got some weird character that are adding in the script, and you're like, okay, that's very funny. And I finished this answer with this. We found two solutions. When it's possible, when you can use SSD driver, which are more stable and that doesn't corrupt so often like the SD, or you can turn your SD card in read-only mode. It means that all that contains the SD card is charged into the RAM, and then you don't have this problem anymore, because if you've got issues on the script, it just disappears when you reboot the system.
Perfect, thank you. So I think we have also a question online, Chantal, right? Wait.
Could you use already existing meteo stations?
Yes, that's a great question. Okay, so basically, official meteospace stations aren't affordable for research project or things like that. Low-cost stations does not give enough quality with the data, and with that solution, we are in charge of which sensors are mounted on the station. What do we do with the information? What format do we have? What quality do we have? And we can decide ourselves where we want to send the data, which is not quite sure is not always the case with low cost or classical meteo station. But to finalize this answer, the strong part of those of this system is that it's very easily modifiable. So if you want to add new sensors, if you want to send data elsewhere, if you want to drive a motor, a pump, or things like that, it is possible because at the heart of the station you've got a PC. So you got a computer, so you can manage to program it to do exactly what you want it to do. You're not you're not dependent of what other has coded before you.
Perfect. Thank you, Loïc.
Thank you.
Again, a little round of applause. And time to call the next and last speaker. That's Cédric Serugendo from CREM, and he's going to talk about the Maps project.
Thank you, Jérôme.
The floor is yours.
Thank you. Hello, everybody. I will just introduce myself. I'm Cédric Serugendo. I'm working on for the CREM as an engineer, and I will present you the Maps project, which is a web platform. And yes, I will introduce you and talk about this project more in detail. So I will start with a small introduction about what is the goal of Maps, the objective of Maps. The first one is to centralize information and data sets on one place. It's always a real struggle to have a data set spread around multiple websites or sources. So the first objective is to bring all this information together in one place. The second one is to improve the accessibility of this data set, because yeah, we have found the data set you want, but you can access them. It's not really interesting. So this is the second goal, and the third is to ensure the quality of this data set. I will explain in which way we ensure this quality after, but this is the third goal. And the last one is to increase the energy data knowledge, and so we try to make these two tools that I will present afterward user-friendly for a researcher, engineer, and so on. The concepts behind our project is quite simple. We have two layers. The first one is a community. It's a community dashboard. Actually, it's just a place where we can find the dataset you are interested in, and if you need exhaustivity or you search for a particular dataset, you will go on this platform. But if you want to discover a new dataset and need accurate quality check data, if you need visualization or analysis tool, you can go on this data management tool. And the idea is to create a connection between this first layer, this community dashboard, and this data management tool to come from one and go to the other. This is the idea. It's an European project, at 2020 project, where we are 7 partners involved, and each partner are in charge of a specific work package, as you can see. I will not going through this work package. I will let you visit our website if you are really interested in to discover what we do in this work package. So now, as I explained, there is two layers in this project. The first one is the gateway, and the second one is the Dynamaps data management tool. And I will start with a small introduction about the gateway. So the gateway is basically a platform where we can find for a specific data set. We have some filter we can apply to find for publication, research data, data set, and other research results. The process to have this all information bring in one place is quite simple. It's a work done by Opener, which are a project partner of the project, and basically we take all the data set we can find on every open source repository, and Opener will do a work to identify the more relevant data set, and other partner, the Iraq Research Center, managed to quality check a specific data set, and this quality check go through a process that classify all the data set in 3 levels based on the accuracy, the consistency, the completeness, and the transparency. Here are the quality check process that this feature dataset have to pass to be named as quality check dataset. And as you can see, the level 3 are really quality check dataset, and the level 1 is less quality check, let's say. Now I'll introduce you this quality check dataset. We identify 36 quality check dataset, and you can go on the gateway and find this dataset and all metadata related to this specific dataset. Actually, I suppose that you know that there is a lot of solution to search for datasets, and it's quite easy to find the dataset you want. But here we have a quality check dataset, but we need to have a better solution, because that we don't have the possibility to visualize the data we found, so we cannot say that it's a good dataset or not. And we need also a simple tool to just analyze quickly the dataset we have, and to have a better appreciation about the quality of the datasets. That's the 2 points missing in the gateway, and the solution was to create in parallel the data management tool, which provide this functionality. So as I said, the purpose of this platform was to allow the user to visualize the dataset they select. Here I just select the heat demand, and you can see, for example, in the big city like Paris or London, there is a high demand, which is quite logical. But the visualization part is not sufficient. We also need a small calculation module to take the dataset more precisely. To do so, we need to select, as Giuseppe showed before in the morning. We select just an area, and in this area we decide to run a calculation module. I select the heat demand calculation module that search the potential of district heating in specific area. Here it's just a module that use 2 thresholds. The first one just remove all the pixel below a certain value, And when we do that, we get an area, and the second threshold just check if this area, the sum of the value of this area are below a certain value or not. And as the output, we have a graph. We have graph, as you can see. The graph shows the potential of each zone, and we also have a layer that show us where is the zone we are talking about. Once we have this result, we have the possibility to just download all the dataset and play with the result in a QGIS tool, or just to process all the information we retrieve from this calculation module. I'll introduce you the concept of the gateway and the NMAP data management tool, and I don't talk for the moment about the connection we have between these two tools. So when we are on the data management tool, we have the possibility to go to the gateway and retrieve all the metadata related to the data set we are visualizing on the data management tool. And once again, we have the possibility to download this data set and just process this data set in a QGIS tool with the process that we already prepare. As a conclusion, I will just say a few words about the interest behind this projects. So the first one is that all the data sets you need are centralized in the same place, so you just have to go in the gateway, and you will find, based on the keyword you select, the data set you need and the metadata related to this data set. We also have the possibility to have a tool that allows us to visualize and analyze the quality check data set. And the tools are really easy to use and can be used by any user going to the engineer, the researcher, to the policymaker, for example. So thank you for your attention, and I remain at your disposal if you have any questions.
Thank you, Cedric, for this presentation. Do we have any question from the audience? René, of course.
Yeah. You know, I don't know so much, so I need to ask. So you have a very good project and very nice idea here, by the sense that, well, everyone collected data, and now we all have them sometimes and find them. You mentioned several times that it's about the quality data sets. Do we have a notion of data quality in these sets that is valid for more than the project for which it was collected?
Yeah, actually for the quality check here, we have several criteria that told us that there is the data set we select is a good data set. So there is a different level. So as you can see, the first one is not high level, and the last one is really really high standard level, I will say. So in this standard, we can see that we go even through the comparison with the similar data set and see if there is there is consistency between these two data sets. So with this quality check, we assume that the results we have at the end are relevant, I would say. Is it the answer you expected? No?
Thank you. Maybe we have the coordinator of the project in the room. Do you want to add something about it?
I think first of all, the
wait.
Yes, So thank you, Cedric, for the answer. I think it's absolutely correct. And I think that's a big challenge to pass from project-wide data validity to general data validity. Because when you do those statistical tests and you compare data sets, I mean, you always have a specific objective, which is more or less linked to your project. So it's very hard to break out of this on one part. And the other part, however, it's quite interesting, I mean, to just introduce the metadata in a sense of completeness and so on, criteria to index correctly the data set, because this is already often something that is missing and that really doesn't help, because you, for example, then you don't see whether a data set has been updated or not. When there's no metadata on it, you suddenly realize it's different than before, but what changed is not really given, and then maybe all of your results change based on the tool chain that you have. So the topic is very complex, and we do not pretend to have the unique solution, but we have a brick that is able to construct, I think, a first piece, and we try to put it out there as complete as possible and as far as we could go. If you have more input, we're happy to listen.
Thank you. Do we have another question in the room? Yes?
Hi. So the way I understand, mostly now it's focused on heat demand or like generally demand maps. There is also potentials in there for PV or maybe other energy. So
actually,
you can comment on the future development or something.
Thank you for your question. Actually, I showed just the heat demand layer, but in the platform, which are online actually, we have a lot of type of data. We have wind energy, solar energy, a lot of data related to energy, but not only heat demand map. Maybe there is a question.
So I think the coordinator wants to add something again.
Well, just yeah, you can find it on our website, and via the open air portal, the sets that are online. Just would like to maybe point out as a little experience made now. When you see those three levels, I mean, you think you can check data, and what we want to put online is fair data, and the fair is also reusable, which sometimes brings a real big problem, because you have good quality data out there somewhere from, for example, an international agency or something like this, but they put a license on this that does not allow us to redistribute the data, so we cannot list it in this way. So just to be aware that there are more data sets out there that also would pass the quality check, but we cannot redistribute them because the people intentionally or unintentionally did not put or did put a restrictive license on this, which disqualifies for being fair data, which is a bit of pity, but that actually happens quite often, I'd say, because, well, the hurdle of exchanging data is low technology-wise, but now sometimes people add legal burden there, so that you have to make an agreement with them so that you can use the data, which is... So some of the data sets that we wanted to include got kicked out this way.
Do we have one last question, maybe, just before closing this afternoon? No more question? Okay, so I think we can thank Cedric again with a round of applause. And again, I would like to thank you all for your presence this afternoon. It's been a long morning, let's say, and I hope you enjoyed this workshop. And of course, I'm looking forward to the next one, which will happen hopefully in 6 months, and that will be related to energy. We had a lot of interesting discussions today, especially with the people from HGSSO, and we are thinking of organizing something similar related to energy, maybe on a more regular basis, something like every 2 years, so that we could follow up on the different subjects that we touched today, and so that we can also see each other in a more regular basis. So I think that's what we can say today. And I don't know if somebody, I know Professor Müller left from this morning. I don't know if somebody from HGSSO wants to say also some last words. René, you've been speaking too much. So wait, I'll give you the mic.
So thanks to the organization, and I'm very pleased to see such an event where we discuss a bit more. So with pleasure.
Well, thank you all, and a big kudos to you all for participating to this event. Thank you.